Hello, everybody. Welcome to the second day of Global Webinar on Material Science and Engineering. Looking forward for very good scientific sessions.
Hello.
And first speaker of today is Dr. Dariusz Jakobczak. He's from Koszalin University of Technology, Poland, and he's going to give a talk on interpolation and extrapolation of curves and functions. And I request Dr. Dariusz to start his presentation.
Yes, good morning from Poland. It's okay. Do you hear me? Do you see my presentation?
Yes. Please
continue. Okay, so I put. Okay, very good. Good morning from Poland. I will speak about some mathematics and applications of interpolation and extrapolation. Not only functions, but also we can have, for example, a contour, closed curve in computer graphics or in engineering, in science, our data. Yes. And also our data are not only 2-dimension, but more. Also, I will speak about more dimension. Here is main entrance to my university in Koszalin, Poland. Some faculties, my faculty is electronics and computer science. Poland, map of Poland. Here is my city Koszalin on the Baltic Sea. Yes, here is Baltic seaside. Not very big city, 100,000 of people, but what about interpolation and applications? For example, we have some cities, yes? If we would like to draw a simple schema, we could connect as a straight line, yes, as a schema. But of course, roads are not a straight line. So what about modeling of data? Yes, of course, here are true in a real roads of real life, but if we have some points, we would like to draw a curve or a function from one point to another. So how to model our data, our points? In 2-dimension, in classical interpolation, we have some nodes, interpolation points, and there are in mathematics polynomial interpolation. Yes, Newton polynomial or Lagrange polynomial or others. But polynomials are not always very good. So one sentence. If we want to calculate data between known points, we have interpolation, yes, and outside our points, we have in mathematics extrapolation. So in 2-dimension, we have our known points, known nodes, and modeling of first coordinate x is simple. Yes, between two successive nodes, we have parameter alpha between 0 and 1. If alpha is 0, we have this node. If alpha is 1, we have second node. Yes, of course, interpolation means exact value in nodes. But what about second or maybe more coordinates? Calculations for unknown values are here. It consists of two parts. First part is almost the same like here, but not alpha, but gamma is function of alpha. Yes, this is modeling function of parameter alpha. And second part connects with combinations of nodes. Here is some combinations of nodes. In the simplest way, this combination could be 0. Yes, if this combination is 0 is the simplest. But sometimes to have better interpolation or extrapolation, we can here use some combinations of nodes. And of course, if alpha is 0, gamma must be 0, yes, to have exact value. If alpha is 1, gamma must be 1, like here. So modeling functions gamma is any strictly monotonic functions from point 0, 0 to 1, 1. And there is infinite number of such modeling function. Yes, here is our formula, and each of this function, if alpha is 0, then gamma is 0, and if alpha is 1, gamma is 1. Yes, to have exact value in nodes. What about the simplest linear interpolation? Here is, yes, power function. If s is 1, if gamma is equal alpha, here alpha, we have the simplest linear combination. And any others data could be modeled using modeling function. Here is, for example, exponent function 2 power x modeled by, as I said, combination of nodes 0 and modeling function, like here. But this exponent function could be also modeled by polynomial interpolation. But what about some examples, some classical examples where polynomial interpolation is not very good? Yes, like here. For example, we have a function 1 divided by 1 plus square x, red graph. Here is 6 nodes, 1, 2, 3, 4, 5, 6. For 6 nodes, we have polynomial rank 5. Yes, and this black polynomial is completely different than our function. It's unused. Also here is 5 nodes. Polynomial degree 4 also is completely different than our function. Yes, so first example is for this function. And in many applications, our data must be smooth in each point. It means smooth in all nodes. For example, here is nodes x0 value 1. Here is x0 value 1 and three more nodes, x minus 1, x minus 0.5, and x1. So 4 nodes, polynomial rank 3. Here is polynomial rank 3 calculated, and here are my calculations. That yes, value of my 2-point smooth interpolation, and comparing errors in some points. Left part here is for left part, for some points for x, like here, and left part maybe even assuming errors, polynomial is some better, but right part from 0 to 1, x from 0 to 1 in 10 points, yes, polynomial assuming error is huge error in this point, 0.9, and my calculations give much better interpolation. So this function as a whole from -1 to 1, yes, left part is and right part is modeled by sinusoidal modeling, this function gamma, and why such parameters s for left part and s for right part. These parameters s are because we want to have smooth function in node 0, 1. Yes, smooth function is done by comparing left and right derivative. Yes, in this point 0, 1, left derivative and right derivative are calculated the same, and in point 0, 1 derivative is extremum, so so derivative is simply 0. If we don't want to have smooth function, extra interpolation is better, yes, without assuming smooth function for right part. Extrapolation is better for this parameter. And what is dangerous in classical polynomial interpolation? Here is a mathematical formula for error in polynomial interpolation. And what is very dangerous? Big M, it is supremum of derivative rank n+1. If we have n+1 nodes, it is derivative rank n+1. here are nodes x0, x1, xn, and generally it is impossible to to control derivative rank n. For n nodes, it is impossible to control derivative rank n for our range of x. And as we see exponent function 2 power x, it also could be modeled by polynomial. Yes, here is calculated polynomial error for four nodes for x1, 0, 1, 2, 3. Derivative rank 4 give here is and give us here this error as whole give is okay, but eighth power x, it is impossible to have such huge interpolation error. Yes, derivative rank 4 for this function. Second classical example is 1 divided by x. Yes, also 4 nodes for x 0.5, x1, x2, and x4. 4 node polynomial rank 3 is completely different than 1 divided by x. And also, for example, to have smooth in all nodes, for example, in this node, from 0.5 to x2 is left part, modeling by power function, alpha power and such parameter n's, and right part. Right part also is not ideal. There are no ideal method, but for example, between 2 and 4, yes, comparing error of polynomial and my smooth interpolation here is better, and left part also less error. Without smoothing, we have better interpolation. And module absolute value function, also 4 nodes. If we treat this function as one curve, one function between -2 and 1, and having 4 nodes, we have derivative rank 3. And in my interpolation, 4 nodes give us simply linear modeling alpha power 1, linear interpolation as a whole curve. Of course, for example, we in polynomial, of course, we could divide our curve for left part and right part, but as these 4 nodes give us this polynomial rank 3. So comparing 4 examples, exponent function 2 power x is okay for polynomial, even better. But second classical examples, polynomial error is bigger than my proposition 2-point smooth interpolation. In computer graphics, in some many applications, there are cubic splines, but also there is a danger because of extremum between the nodes. Yes, we don't want to have unknown extremum between the nodes, and using polynomials. Yes, cubic splines are polynomials rank 3. Generally, we don't know if extremum exists or doesn't exist. It is unknown. Our data, my proposition is parametric form of curves. Yes, parameter alpha, like here, parameter alpha, first coordinate, second or more. Why? Explicit representations give us only function. Yes, in explicit representation, we couldn't model any closed curve or any curve, for example, vertical line or circle. It is problem. So explicit representation as formula of function, it is rarely used in many applications. Implicit representations give us also formula for function equals 0, but sometimes it is different. Having x, for example, calculate second value. So the best is parametric form of curves. So our data in many engineering applications where, for example, formula are very complicated, formula of functions could be very complicated, or very high complexity of calculations, there is necessity of modeling via simple functions. So having our data, we want to have modeling functions gamma the best, where the error is minimal. And second part, as I said, like here, formula for combinations of nodes 0. Some examples of combinations of nodes, for example, like here. As I said, no matter if the curve is open or closed, so our data could give us a contour of object, a closed curve. And extrapolations. Extrapolations is when alpha is outside range 0, 1. If alpha is less than 0 or alpha is more than 1, our calculations give us values outside our range. Yes, if alpha is between 0 and 1, we have interpolations. And this extrema is that because these calculations are for some combinations of nodes, for example, like here. Yes, it is danger. If combination of nodes is 0, like here, we are absolutely sure that there will be no extrema between the nodes. Yes, like here, there or like here, no extremum between the nodes, or like here. Yes, in polynomial, for example, here is minimum or maximum between the nodes. So applications in engineering science in where when we have many data, for example, a curve of motions, a human body contour, or a line in fingertips needs modeling, gesture of movement modeling. What about more dimension? For example, X, Y, Z, third coordinate, third value also could be modeled by another modeling function gamma, gamma 1. One function gamma, second value, different function gamma for third value, and combination 0. So for more dimension, yes, also third, fourth, fifth coordinate, third, fourth, fifth value could be modeled by other modeling function gamma. And for example, in image interpolation, yes, when we have one pixel, second pixel, and for example, grayscale, yes, grayscale between two pixels, number in grayscale could be third value, third coordinate, and in image zooming or warping on or image interpolation for grayscale or for color, yes, for color we have more values. In grayscale we have one number for grayscale. In color picture we have more values. Curve fitting, modeling, data reconstruction, image retrieval. In classical numerical analysis, there is need to interpolate data values in many engineering problems. And in the end, here are some of references, some of books when you could find informations. Last book is Finnish, Analyzing Data Through Probabilistic Modeling in Statistics. Also, you can find it. Here is view of my city. As I said, here is Baltic Sea. Main entrance of my university, cathedral. And here is also my university, some buildings of my university. And before I thank you, one applications. Here is example, yes, having some nodes. Here are our modeling function. For example, here is power function, sinusoidal function, and so on. For parameter S, alpha power 1, the simplest, yes, linear. If we change parameter S, we can change convexity. Yes, we could model convexity of our data. And in these examples, for each pair of nodes, here is the same modeling function. Yes, but as I said in my presentation, for between each pair of nodes, we can change modeling function. Yes, in my presentation, I talk about that for each pair of nodes, we have different modeling function to have the best interpolation or to have smooth. But in this simple examples, yes, for each pair of nodes is the same. And combination of nodes 0. Also, I can have any graph or closed and, for example, tangent, or maybe 1, 2, maybe too many, 5. Closed curve for and so that's all. That's all. Thank you for attention. If you have any questions or remarks, thank you very much.
Thank you, Dr. Darius. Thank you for the excellent presentation.
Thank you.
We are open to questions.
Thank you.
Anybody has questions? Can ask Dr. Darius.
If you don't mind, I would like to ask a general question.
Yes.
Thank you, first of all, for your very nice talk. And it is always good to have people who come from mathematics when we are doing research in material science and engineering. I have a very, very general question since about I'm sorry that it's maybe not directly related to the talk, but I'm simply just curious a little bit. And I'm thinking about the concept of fractal geometry. Fractal geometry is something that I have seen every once in a while in material science being applied in, for example, fracture mechanics.
Yeah.
As well as, for example, in the description of porosity, porous systems, and so on. And if you don't mind, I would just simply put the question like this: if you would like to give a comment or maybe a little bit of an update about the status and the applications of fractal geometry in material science for today. And yeah.
Yes, sorry, but I haven't yet used fractal geometry, so I have not many information about fractal geometry. So
That's okay. I'm
So
sorry.
yes,
Private
I'm not friend in fractal geometry, so I
Okay,
don't
okay,
want.
okay.
Okay,
Perfect.
Yeah.
Thank you.
thank you.
Okay, thank you. Thank you, Dr. Darius. Thank you for your presentation.
Thank you.
Just one more clarification I want.
Yes, yes, please.
Yeah. Good morning, Professor. Can you hear me?
Yes.
Yes. Good morning. Very nice presentation. I just want to know that during the interpolation and extrapolation, the nodes that you are considering, the length between the nodes, do you consider equal length throughout your analysis, or
Yes, it could be used in numerical analysis, in mathematical applications for simple numerical interpolation of curve. Yes, it could be used.
could be, but when you are considering this sinusoidal and all those exponential functions, the interval length, whether it is equal interval length or unequal interval length.
Sorry, could you repeat?
In your modeling,
Yeah.
you have considered sinusoidal exponential functions.
Yes. Yeah.
Okay. Now, when you are locating the nodes, the length between two nodes are equal length or they are unequal length.
Yes. Nodes more could be unequal. Could be unequal distance. Yes, you talk about distance between the nodes.
Yes, exactly.
Yes. The nodes could be any. If we have any true data, it is not necessary to have the same distance between the nodes. The nodes could be any data we have.
But when the curve takes the different shapes, so that time it requires unequal, is it? Because your modeling includes the data of curves instead of, if you have a straight line, yes, as you told, if we are know the length, then we can go for equal. But in your modeling, you are considering a model and you are fitting your function. So when you are taking your model, there are curves in that modeling. So which model you have shown one example for the human being modeling. There you come across a lot of curves. So when you have curves, how do you consider equal nodes, equal length between the nodes, I mean to say?
There is no necessary to have equal nodes. I modeled for true data to have the best, yes,
Okay.
the best interpolation, to have the smallest interpolation error.
You have considered equal length.
Yes, okay, thank you very much.
Thank you.
Thank you.
Thank you, Darius, for answering the question. Thank you so much.
Thank you.
And moving forward, our next speaker for today is Dr. Abir Sweden from IEM in France, and she is going to give a presentation on nanostructured materials and their application as enzyme mimics for bacterial fighting.
Good morning,
And I
everyone.
request Dr. Abir Sweden to start her presentation.
Okay. Good morning, everyone. Good morning. You can hear me?
Yes, yes, yes.
Okay. So first of all, thanks all for being here today. My name is Abir Swaidan. I have a PhD degree in nanomaterial sciences and nanotechnology from France. So today I'm gonna speak about the synthesis of nanostructured materials and their application as enzyme mimics for sensing and bacterial fighting. Actually, my interest in enzyme mimics lies on how we design a technology in the nanoscale form and how nanotechnology can be tuned to be more in accordance with environmental and the human requirements. Sorry. Okay. So first of all, we did the synthesis of composite nanomaterials and nanocomposite. We studied their surface functionalization and modification with various ligands. And also we studied the encapsulation and the release of active ingredients from the functionalized nanomaterials. And the developed nanoparticles were applied for sensing of various heavy metal ions for colorimetric approaches. And also the developed nanoparticles were applied for the eradication of bacteria and also for chemophotothermal therapies under near-infrared irradiation. First of all, I'm gonna give the meaning of natural enzymes, their mode of action, their industrial application, and then I'm gonna elaborate on some issues encountered with these natural enzymes, after which I'm gonna shed light on two central points, mainly the artificial enzymes, which are re-engineered enzymes, and then I'm gonna shed light on the nanozymes, which are natural enzyme mimics, how these agonists works, their fundamental applications, and finally the CUS-based nanozymes. And at the end, I'm gonna give a brief conclusion. So first of all, what are enzymes? As we all know that enzymes are globular proteins that are made up of amino acid residues and incorporating a small region, which is called the active site. Actually, all enzymes, they have the active site in their structure, and this active site can bind to a specific substrate in order to release the desired product. A typical example is horseradish peroxidase. Horseradish peroxidase is a naturally occurring enzyme that has iron in its trivalent state in its catalytic site. So in the presence of hydrogen peroxide, the horseradish peroxidase can convert the hydrogen peroxide into hydroxyl radical via the oxidation of certain chromogenic substrates, such as the tetramethylbenzidine, for example, via one electron transfer. So in the presence of this chromogenic substrate and horseradish peroxidase and H2O2, TMB can be converted into a charge transfer complex. And actually, which is in equilibrium with a free radical form. And this form is can be monitored like quantitatively and qualitatively through displaying an absorption maxima at 654 nanometer using UV visible absorption spectroscopy, and also by displaying a blue colored oxidized product. So normally TMB is colorless, and once it is oxidized, it can generate a blue color. So it can transform into a blue color. So natural enzymes, they have several advantages. Actually, they have a substrate specificity. They can catalyze a wide variety of reactions with a fast reaction response. They have a huge specificity. They have also high catalytic efficiency, and they are environmentally friendly, non-toxic, and biodegradable. These advantages enables natural enzymes to be used in wide variety of industrial applications. For example, natural enzymes can be used as antibiotics. Example, lysozyme and alginate lyase, they can be used for environmental protection for the removal of certain waste, for example, pesticides in water. They can be used in biosensors, for example, to detect certain disorders in the body, also in fuel cells, food beverages, and also they can be used as an animal feed additives. Although promising, natural enzymes are prone to certain drawbacks because actually they are degradable when the conditions are unfavorable. So under harsh conditions, natural enzymes are prone to degrade, and also their extraction is time consuming and represents a high cost. So scientists thought of re-engineering these natural enzymes through 3 different steps, either by immobilizing the natural enzymes on solid support, or by chemical modification of certain functionalities, or by genetic mutation to introduce unnatural amino acids in their catalytic site to enhance their enzymatic activity. Actually, this step is very promising because a natural enzyme is chymotrypsin, and once it's functionalized with calcium phosphate in order to generate a nanobiocatalyst, the proteolytic activity of this natural enzyme is enhanced. Although promising, re-engineered enzymes also possess certain drawbacks. Actually, they need experts, especially in the genetic mutation, and also it is very expensive, and sometimes there's an enzyme leakage, especially in the immobilized form. And in terms of chemical modification, sometimes it could be non-specific and time-consuming. So there's a great demand for the development of new alternatives to these natural enzymes that exhibit the attractive properties of these natural enzymes and yet overcome their aforementioned drawbacks. So scientists developed new alternatives under the name of nanozymes. Actually, these nanozymes have unexpected enzyme mimicking catalytic activity. Nanozymes are even could be organic or inorganic nanocomposites and nanomaterials that can mimic the catalytic site of natural enzymes. For example, they can mimic a wide variety of natural enzymes such as catalase, oxidase, peroxidase, superoxide dismutase, among others. And especially thanks to the nanotechnology, where one can develop nanoparticles with tunable properties in order to enable them to be used in a wide variety of applications. Actually, these nanozymes possess a huge interest over natural enzymes because they can be synthesized with a low cost, and actually they showed high stability, and they can be synthesized with different structures and with tunable activity. A typical example is the development of a biomimetic dual inorganic nanozyme, which is made up of mesoporous nanostructures of gold and iron oxide functionalized with a specific polymer polyethylene glycol nanoparticles in order to render them stable in an aqueous environment. So as you may know that glucose oxidase is a natural enzyme that is responsible to convert glucose in the presence of oxygen into hydrogen peroxide. So the presence of gold nanoparticles can generate hydrogen peroxide, and also the existence of these iron oxide nanoparticles through the Fenton reaction, they can generate hydroxyl radicals. And once applied to the tumor microenvironment or even to the cells, these nanoparticles can enter the cells via endocytosis, and once inside the cells, in the presence of hydrogen peroxide, they can generate hydroxyl radicals, which is responsible for mitochondrial damage, also double-stranded DNA breakage, and finally, which led to apoptosis. So actually, as we know that nanomaterials are the key components of nanotechnology, and when we focus on their fundamental intrinsic properties, nanomaterials can be synthesized with various properties. So among myriads of nanomaterials, we use the copper sulfide based nanomaterials because these nanoparticles, they have a low cost, they can be easily synthesized, and they mimic the naturally occurring peroxidase enzyme. They can be easily attached to other nanoparticles, and most importantly is that they absorb in the near infrared region. However, all nanoparticles, they tend to aggregate, so their surface modification is very important. Through modifying these nanoparticles, we were able to synthesize the CUS with bovine serum albumin protein, and then with the further functionalization with the copper phosphate, we synthesize another nanomaterials, which are copper sulfide BSA copper phosphate nanoparticles. So the successful synthesis of the nanomaterials has been confirmed by various characterization techniques. We use UV visible, TEM, SEM, XPS, X-ray photoelectron spectroscopy, FTIR in order to confirm that these nanoparticles, they are attached together, and also we used SEM. So the synthesis of these nanoparticles has been applied for colorimetric sensing assays of the hexavalent form of the chromium. As you may know that chromium exists in various forms, and the most stable forms are chromium 6 and the chromium 3. Actually, chromium-6 can enter into the cellular membrane via because it resembles the sulfate and phosphate channels. And once inside the cells, it can be converted into chromium-3. So once it is converted to chromium-3, it can form an adduct with the double-stranded DNA, causing its breakage. Also, it has another mechanism, is that it can generate hydroxyl radicals if hydrogen peroxide exists, which also causes to single-stranded DNA breakage and finally led to cell apoptosis. Due to these disadvantages, there's an urgent need for the detection of a hexavalent form of the chromium. And among various techniques, we choose the colorimetric sensing assay due to its simplicity, and also it represents a low cost without the need of any sophisticated instrumentation. So chromium-6 has been detected by using nanomaterials that mimics the naturally occurring Horst-Radish peroxidase. So by monitoring the production of the oxidized product, TMB, and by recording the absorption maxima at 654 nanometer, we confirmed that the TMB is oxidized due to the generation of hydroxyl radicals from the chromium-6. We also extended our work field through the sensing of various biological molecules such as glucose and dopamine. And actually, as we all know that the glucose concentration is the key indicator about the patient's health quality. So glucose concentration should be monitored frequently in order to avoid complications associated with hyper or hypoglycemia. We all know that the glucose can be detected using the glucometer. However, we found that the colorimetric sensing assay is very simple in detecting glucose. So by using two different nanoparticles for sensing glucose, actually we used glucose oxidase to generate hydroxyl radicals, and in the presence of our nanoparticles, the hydroxyl radicals can be converted into the hydrogen peroxide can be converted into hydroxyl radicals, which in turn can oxidize the TMB to produce a blue-colored product. We've noticed that CUS-BSA, when they were functionalized with copper phosphate nanoparticles, they generate a higher absorption maxima over the CUS-BSA due to the presence of excess copper ions on the catalyst surface. And among myriads of nanomaterials, our nanoparticles, they represent the high sensitivity towards sensing glucose because they possess a low detection limit. And also, we determined the selectivity of our nanoparticles for detecting the glucose by using several glucose analogs. And we noticed that from the blue color oxidized product here, that the nanoparticles, they have high ability to detect the glucose in the presence of other analogs. We also studied the biocompatibility of the developed nanoparticles through the hemolysis test, and we've noticed that they are highly biocompatible, which can be also applied in vivo and in vitro. However, one should do also the cellular toxicity assay. These advantages inspired us also for the detection of dopamine. And however, dopamine can be used in various things. Actually, it can be added to animal in order to help them build muscles. So once dopamine reaches a huge concentration in the body, it can cause several disorders. So the detection of dopamine is essential. And by using our nanoparticles in the presence of hydrogen peroxide and dopamine, we've noticed that dopamine can quench the hydroxyl radicals and can turn the blue oxidized product of TMB into colorless one. Okay, so the biomedical part can also benefit from the fundamental properties of these nanozymes because they have the ability to generate reactive oxygen species, especially the hydroxyl radicals. Okay, so as we all know that bacterial infection represents a huge threat to human health, and currently the use of antibiotics remains the choice of interest. We all know that antibiotics can cure the patient somehow. However, there's also spread of bacteria, and bacteria can cause resistance as well to drugs due to the improper use of antibiotics. And also, especially that drug resistance is being increased nowadays when the new drug development has been declined. So multi-drug resistant bacteria has reached an alarming level. So it is a worldwide catastrophe that has to be treated soon. So researchers have thought of modifying the existing antibiotics, and this didn't work much. So they thought about the development of nano antibiotics. Either they use the antimicrobial peptides, or they can use the existing antibiotics conjugated with nanomaterials, or they use the nanomaterials as antibiotics themselves. So by the help of a physical external stimulus, such as the near-infrared irradiation light, once these nanoparticles applied to the cell, they can enter the cell via endocytosis, and in the presence of NIR laser, these nanoparticles can cause the generation of reactive oxygen species, such as singlet oxygen, in which it can cause the disruption of the cellular membrane or even the degradation of the DNA structure. And this is called the photothermal therapy. However, the generation of reactive oxygen species is called the photodynamic therapy. So photodynamic therapy utilizes the use of light-sensitive molecules that can use the light in order to absorb the light energy into oxygen molecules to generate reactive oxygen species. So by the help of PDT and PTT, which is the photothermal therapy and the photodynamic therapy, we showed like a huge advantages over alternatives for the treatment of bacterial infection, because by using PDT and PDT, one can have a deep tissue penetration of these antibiotics, so antibiotics can reach the target without a premature release, so they can reach the target without being cleared from the body. And also they can improve the brain permeability, enhance the drug stability, enhance the antibiotic cellular uptake, and also it minimizes the antibiotic doses. So we used copper sulfide based nanoparticles because these nanoparticles, they have the tendency to absorb the near infrared light and to convert it to heat. Because copper sulfide nanoparticles, first, they can generate a reactive oxygen species, they can induce hyperthermia, and also they have a strongest binding affinity to the bacterial membrane. And also we used NIR light with these nanoparticles in order to load a natural antibiotic, which is lysozyme. So by loading lysozyme to the CUS-BSA nanoparticles and by the use of NIR light as an external physical stimulus, once this light is applied, the lysozyme can be detached from the nanoparticles and reach the cellular membrane of the bacteria and causes its eradication. So the successful loading of the lysozyme has been detected by using zeta potentials. So these nanoparticles, they possess a negative charge, and once lysozyme has been attached to these nanoparticles, this charge has been transferred into a positive charge. So in this way, we can confirm that the lysozyme has been loaded in our nanoparticles. We also studied the photothermal heating performance of the developed nanoparticles by using the NIR light at two different laser power densities, and we used nanoparticles with different concentrations. So by applying this light, we've noticed that with increasing concentration, the temperature response has been increased. So this indicates that our nanoparticles, they are excellent photothermal they have excellent photothermal properties. We also studied the cellular viability of the developed nanoparticles on cancer cells. So we used HeLa cells and also we used U87MG cells. We used nanoparticles with different concentration, without laser, with laser, and with the loaded antibiotic and without the loading antibiotic. So we've noticed that at around 100 microgram per ml, the nanoparticles with and without the lysozyme, they didn't induce toxicity to these cells. However, at higher concentrations, a dose-dependent toxicity was observed. So we stopped around 100 microgram per ml. So this indicates that our developed nanoparticles are highly biocompatible, which can be used further in vivo. So these nanoparticles were used for bacterial eradication of two types of cells. Actually, we used a gram-negative E. coli bacteria, and we used the gram-positive E. coli bacteria because both bacteria, they have different cellular structures. So by using the laser at two different laser power densities, as we can notice here, that in the presence of the nanoparticles loaded with the antibiotic and by applying higher laser power density, we've noticed that the bacteria is completely eradicated, especially at higher concentrations. However, we've noticed that these nanoparticles, they were less effective to gram-positive bacterial strains because actually the lysozyme cannot had more effect on the gram-positive bacteria. So CUS BSA lysozyme can result in considerable reduction in bacterial viability, and they possess a stronger bacterial killing efficiency to gram-negative bacteria instead of gram-positive bacteria. So to conclude up, we developed an environmental friendly low-cost nanomaterials that has been functionalized with bovine serum albumin protein in order to enhance their stability and to be used in the aqueous microenvironment. And we also, the synthesized nanoparticles were shown to mimic the naturally occurring peroxidase enzyme in the ability to generate reactive oxygen species such as hydroxyl radicals. And also these nanoparticles, they proved to be novel antibiotic carriers that can be used under near-infrared irradiation for bacterial eradication. Okay, thank you.
Thank you so much, Dr. Abis Biden. Thank you for your excellent presentation.
Okay,
Any
thank
questions
you.
for Dr. Abis Biden? And next speaker for today is Professor Osman Adigüzel from Firat University, Turkey, and he is going to give a talk on reversibility and nanoscale aspects of phase transformations in shape memory arrays. And I request Professor Osman to start his presentation.
Thank you very much. Can I share my presentation?
Yes, please.
Yeah, thank you. Hello, it is okay?
Yes, please continue.
Yeah, thank you very much. Good morning, good afternoon, and good evening to all at the conference from a different location on the globe of the world. Let me inform you that this is a multidisciplinary conference from biomedicine, biomaterials, to material science and basic sciences. I am sure you agree with me that this is a multidisciplinary conference and every scholar is not familiar with every subject of the science. Therefore, at the beginning of my talk, I'll introduce the basic terms and definition related to the shape memory effect and martensitic transformation. Let me take a photo, please. As you can see, the title of my presentation is Reversibility and Nanoscale Aspects of Phase Transformations in Shape memory alloys. Shape memory alloys are thermoresponsive materials and exhibit a peculiar property called shape memory effect. This behavior is initiated by cooling and deformation processes and performed thermally on heating and cooling. These alloys can be plastically deformed in low temperature condition and record the original shape just by thermal means on heating or the reverse austenitic transformation temperature after removing the strain. These materials cycle between deformed and original shapes on cooling and heating in the bulk level. These alloys exhibit another property called superelasticity, which is performed by magnetic stresses in a constant temperature. Therefore, these alloys exhibit dual thermoelastic and superelastic characteristics in memory manner. This is main processes for shape memory effect. This is parent phase structure of material in the austenitic state. As I mentioned, the first step is cooling in the shape-memory effect, and on cooling, the shape of the material doesn't change, but crystallographic transformations occur in the atomic level. Second step is the deformation. This is a plastic deformation, and the material keeps the deformed shape after releasing. And on heating, material recover the original shapes and cycle between original and deformed shape on heating and cooling in the reversible way. Shape memory effect and superelasticity is the result of the crystallographic transformations, thermal and stress-induced multisystem transformations, and evaluated by the structural change in atomic scale. Shape memory effect is performed thermally in a temperature interval depending on the forward Austenit-Martensite and reverse Martensite-Austenit transformation on cooling and heating. Superelasticity is also performed in the current phase Austenit phase region and just above Austenit phase temperature. For the superelasticity, the materials are deformed in the current phase region and shape recovery is performed instantly and simultaneously upon releasing the applied stress. This is temperature hysteresis of shape memory effect. As I mentioned, first step in the shape memory effect is to cool, and on cooling, martensitic transformation, thermal induced martensitic transformations start at MS temperatures and completed MF temperatures. MS means martensite start and MF is martensite finish temperatures. Reverse austenitic transformation, austenitic transformation start at AS and completed at AF temperatures. AS and AF temperatures are austenite start and finish temperatures. Over the AF temperature, the material is completely in the parent phase region. This is stressity and characteristics in shape memory effect and superelasticity. As I mentioned, the second step is the deformation in the shape memory effect. As you can see, early stage of the deformation in shape memory effect and superelasticity exhibit ordinary elastic material behavior. And stress-induced martensite transformations occurs in the plateau region in the shape memory effect and superelasticity. As you can see, in the superelasticity, stress and releasing paths are different, and this hysteresis lobes refers to the energy dissipation. This is another strain behavior of shape memory alders at a temperature between martensite finish and austenite start temperature. As you can see, this profile exhibit another property beyond shape memory effect and superelasticity. This is another illustration of shape memory effect and superelasticity. In the shape memory effect, the material is deformed at the product martensitic condition in the low temperature condition. Upon releasing, the material keeps the deformed shape due to the plastic deformation, and on heating, the material recovers the original shape and cycle between original and deformed shape on heating and cooling in the bulk level. In the superelasticity, the material is deformed in the low temperature condition, and upon releasing, the material recovers the original shape by means of reverse austenitic transformation. Shape memory behavior is evaluated by the microstructural change in atomic scale or Angstrom level caused by the internal stresses, and shape change occurs in the macro level. Martensitic transformation occurs in material is thermal manner on cooling from high temperature Fahrenheit region, and it is characterized by change in the crystal structures of material. Martensitic transformations are lattice distorting fast transformation and occur as student martensite with cooperative movement of atoms over very short distances on the order of angstrom by means of shear-like mechanism. And the twin martensitic structures turn into the determinate martensites or reoriented martensite by means of strain-induced martensitic transformation applying external stress. This is the schematic illustration of shape-momery cycle in the crystallographic level. Let me inform you that shape-momery effect and superelasticity is observed in the beta phase region of the material at the first diagram. And ordered crystal structures are essential. On cooling, ordered parent phase structures turn into the determinate martensitic structures by means of thermal induced martensitic transformation. And with the deformation in the low temperature condition, twin martensitic structures turn into the determinate martensitic structures by means of stress-induced martensitic transformation. And on heating, the material recovers the original shape, and in the crystallographic level, determinate martensitic structures turn into the ordered parent phase structures. And on cooling and heating, crystal structures of the material cycle between determinate martensitic structures and ordered parent phase structures in the reversible shape-momery effect. This is the schematic of superelasticity. As I mentioned, the material is deformed in the parent phase region for the superelasticity. With this deformation, ordered parent phase structures turn into the directed to the determinate martensitic structure, which is second step in the shape-momery effect. And upon relation, the determinate martensitic structures turn into the ordered parent phase structures in the superelasticity. This is three-dimensional illustration of shape-momery mechanism in the crystallographic level. First step is cooling, and with the cooling, ordered parent phase structures turn into the twin martensitic structures by means of thermal induced martensitic transformation. Upon the deformation, twin martensitic structures turn into the determinate martensitic structures, and this structure is kept upon releasing, and on heating, determinate martensitic structures turn into the ordered parent phase structures on heating and cooling, and cycle between ordered parent phase structures and determinate martensitic structures on heating and cooling. Superelasticity is also linked with stress-induced martensitic transformation, which is induced by applying only mechanical stress. With this stress, current alternate phase structures turn into the completely determinate martensitic structures, as in the deformation step of the shape-momery effect. And the determinate martensitic structures turn into the parent phase structures upon relation with the reverse alternative transformation. And crystal structures cycle between parent phase structures and determinate martensitic structures on stressing and releasing. It is important that stress strain curve exhibit nonlinear behavior, and stressing and releasing paths are different, and hysteresis lobes refers to the energy dissipation. This is the stress strain diagram for the superelasticity. With the stressing, ordered parent phase structures turn into the directly determinate martensitic structures, and upon releasing, determinate structures turn into the ordered structures, ordered parent phase structures. As you can see, stressing and releasing paths are different, and this hysteresis lobes refers to the energy dissipation. Martensity transformations are first-order solid-state fast transition and occurs in a few steps with the cooperative movement of atoms in this specific manner. Therefore, these transitions have diffusionless character and product Martensity phase inherits the order of parent Austenite phase. Martensity transformations may occur into basic steps in the beta phase region of material. These are Bain distortion and lattice invariant shell. Let me inform you that, as I mentioned, the Shep-Momery effect and superelasticity is observed in the beta phase region of the material. And these are basic BCC-based structures. First is basic BCC body-centered cubic structures. Second figure is cesium chloride type superlattice structures. Third figure is DO3 type crystal structures. This figure is also L21 type crystal structures observed in the ternary copper-based Shep-Momery alloys. Bain distortion is mainly effective in ternary copper-based Shep-Momery alloys and consists of an expansion of 26% in 001 type axis called Bain axis and a compression of 11% in the 110 type direction perpendicular to the Bain axis. Sorry. There are three Bain axes, cube axis, 100, 010, 001, and BCC unit-based unit cells turn into the BCT, body-centered tetragonal structures as trivariant in different orientation. This is cubic structures with the Bain distortion. These cubic structures turn into the three types of the tetragonal structures. Lattice invariances occur as Martensite variants on 110 type planes of Austenite matrix, which is basal plane of Martensite. These cells occur in the opposite direction, 110 type direction on the 110 type planes. The 110 type plane family represents 6 certain planes and totally 24 Martensite variants occur. These plane pairs are listed as follow: 110 minus 110, 101 minus 101, 011, 01 minus 1. Lattice invariance and lattice twinning is not uniform in copper-based Shep-Momery alloys, and these shares cause the formation of layered structures. The 110 type planes of parent phase basal plane turn into the unusual layered structures, which consist of an array of closed pocket planes with complicated stacking sequences called as 3R, 9R, or 18R Martensite, depending on the stacking sequences on the closed pocket planes of the ordered lattice. The periodicity and therefore the unit cell is quantiated through 18 layers in directions that in 18 are Martensite structures. This is the formation of layer structures. This is stacking of 110 type planes of austenitic matrix. Stacking is AB, 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 and with the lattice invariance, the stacking turn into the layer structures with the stakings ABC, BC, AC, AB, A, and others. This is another illustration of the formation of layer structures for the DO3 type ternary copper-based Shep-Momery alloys. These are the basic terms and definitions related to Shep-Momery effect and superelasticity. Experimental studies were performed to copper-based Shep-Momery alloys. These are copper zinc aluminum and copper aluminum mangan alloys. You can see alloy composition of these alloys. This composition were selected in the beta phase region of the material. As you can see, martensit start and finish temperatures are over the room temperatures, and both of the alloys are completely martensitic state at the room temperatures. Specimens obtained from these alloys were solution treated for homogenization in the beta phase field as following, and then quenched in ice brine and aged at room temperature. These homogenization temperatures are 830 and 700 degrees for copper, zinc, aluminum, and copper, aluminum, mangan alloys, and these temperatures were selected in the beta phase region in the phase diagram. Powder specimens for X-ray examination were prepared by filling these alloys, and the specimens were sealed in evacuated quartz tubes and given beta phase homogenization treatment at the same temperature for 15 minutes. Powder diffractorams were taken for all the specimens at the different stage of aging in a long time interval. This is an X-ray diffractoram taken from copper, zinc, aluminum alloy samples after long-term aging at room temperature for about 15 years after quenching. As you can see, diffraction peaks are different, and these peaks this diffractoram exhibits superlattice reflection. It is interesting that at this diffractoram, this plane pair is important: 122, 202, 128, 208, 110, 2010, and others. This is another X-ray diffractoram taken from copper, aluminum, mangan alloys after long-term aging at room temperature for about 15 years after quenching. As you can see, this diffractoram also exhibits superlattice reflection with these plane pairs. A series of X-ray diffractorams have been taken from both of the alloy samples in a long time interval, and some changes have been observed in diffraction angles and peaks intensities and peaks characteristic with aging duration. In particular, some of the successive peak phase have shifted toward each other, and this peak phase provides the following relation between Miller indices. Here is N is 4 for 18 martensite. As I mentioned, these plane pairs can be listed as follows for 18 are structures: 122, 202, 128, 208, 110, 210, 040, 320, and others. At the long-term investigation, it is observed that these peak pairs come across each other with aging duration, and this change reveals the change in the crystal structure of material. Also, this change refers to the rearrangement of atoms in disordered manner in the martensite. These are the electron diffraction patterns taken from both of the alloy samples. This is electron diffractoram taken from copper, zinc, aluminum alloy sample. Second figure is taken from copper, aluminum, mangan alloy sample. As you can see, electron diffraction patterns also exhibit superlattice reflection. As conversion, Shaped-Momer effect is evaluated by the structural change in the microscopic scale by means of martensitic transformation. The fundamental structures of the beta-type martensite are orthorhombic closed pocket structures, which consist of an array of closed pocket planes in the copper-based Shaped-Momer alloys. The beta-type martensites have the layered structures and are characterized by the stacking sequences depending on the order in the parent austenite phase. Copper-based ternary alloys have the deauthorized superlattice in the parent arsenic phase and the following stacking sequences occur with the complete multicyclic transformation ABC, BCA, CAB, ABC, BCA, CAB, and others. On the basis of arsenic-multicyclic relation, the basal plane of 9R or 18R martensites originated from one of the 1-1 planes of the parents on which lattice invariance occurs in two opposite directions during the martensitic transformation. These are the references. Thank you very much for your attention. If anybody asks a question, I can try answer.
Yes. Thank you, Professor Osman.
Thank you very much.
Thank you for your excellent presentation.
I think there is a problem.
Yes.
Can I cannot hear, please.
Yes, we can hear you. Please continue if you want.
Can I finish?
Yes, please. Yes, please.
Yeah, okay. Thank you very much.
Okay, and moving on, our next speaker for now is Mr. Akshat Verma from BITS Pilani, India, and he's going to give a presentation on flame retardant nano coatings for PVC artificial leather. And I request Mr. Akshat Verma to start his presentation.
Sure. Is my screen visible?
Yes, please continue.
Okay, I think there is a problem in my computer links. Sorry.
So, hello everyone, I'm Akshat Verma from BITS Pilani, India, and today I'll be giving a talk on flame retardant nano coatings for PVC based artificial leather, and which was also a part of my master dissertation in BITS Pilani under the supervision of Dr. Krishna Chaitanya Diga, who is an assistant professor in Department of Chemical Engineering in BITS Pilani. So the outline is here. We will first of all we will have an understanding about the artificial leather, and then we'll go about the flame retardants which are employed to improve the flame fire resistant properties of the artificial leather. Then we will go on how the flame retardants are coated. That is by, in our case, it is layer by layer assembly or layer by layer surface assembly. Then we'll move on to my experimental section. Then finally the characterization. And an interesting topic here, which we employed in this study, is corona treatment or corona discharge studies, which were actually used to change or modify the surface properties of the PVC-based artificial leather. Then we will have the American Society for Testing in Materials D6413 vertical flame test, which is the ultimate test employed here to test the flame resistant property of any textile, any fabric. Then we'll move on to the results and finally the conclusion. So we have the artificial leather. Artificial leather, or it is known as in other terms as synthetic leather, fox leather, vegan leather also. It is nothing but a material substituting natural leather, and it has wide range of advantages over the natural leather. Like it is more durable. It never cracks. Although it has its own disadvantages also, like it is much more flammable than the natural leather. It does not allow the moisture to permeate through it. But that is another point of discussion. Artificial leather is generally made of PVC or polyurethane, but there have been, other chemicals used to generate the artificial leather in history. In our work, we employed PVC-based artificial leather for the reasons which I will explain later on. So, artificial leather or PVC based artificial leather, or even it is not a PVC based artificial leather, polyurethane based leather suppose, is used widely in all our seat covers, especially in the trains, in cars. The purse and the wallets we use are generally made of the artificial PVC based artificial leather. The problem in this case is, suppose if a train catches fire, then it is widely noted that the seat covers, they are the one that burn most vigorously. They are the one they burn most vigorously. They even spread the fire. And the worst thing is that since these leathers are made of PVC or polyurethane, they do release some sort of toxic chemicals, suppose like HCl fumes, which can choke people to death if it's in a closed train coach or closed train compartment. So this problem is quite serious, and in my dissertation we try to solve it. So coming on to flame retardants, flame retardants are nothing simple. Simply they are the materials applied to a substrate to prevent or stop the growth of fire. Generally, they are either added as a filler or they are applied as a coating to the surface of the substrate. Coatings are much more desirable over the addition of fillers. There are 2 to 3 reasons. First of all, the fillers when added, they often change the properties of the matrix, which can lead in some difficulty. Like they can change the viscosity, they can change the strength of the matrix if fillers are added. Other thing is that if the fillers are added, they also change the industries. They are forced to change the modification. They have to modify the process parameters. Suppose we are adding a fillers. Suppose we are adding MMT, montmorillonite nanoclay, which is widely used as an flame retardant, which is widely used as a flame retardant in the polyurethane or PVC based matrix. Once we try to prepare the leather, it is definitely going to observe that the parameters have to be changed, because the temperature at which the leather PVC based leather is made will get changed because of the addition of this new filler. But if you are using MMT as a coating, then what we need to do is just add a new step. No more modification is required in the old process. The old process will go along as its way. We will have to just add a new step so that there won't be much disturbance in the old process. There are different sort of coatings, sol gel coatings, passive barrier and intumescent coatings. We are here talking about passive barrier coatings and intumescent coatings. Passive barrier coatings, as shown in this schematic figure, are like that. They do not allow the transfer of oxygen and heat to the substrate, and simultaneously, even if the substrate catches fire, they try to prevent the coming out of volatile gases to the oxygen and heat. Intumescent coatings, on the other hand, they generally themselves burn for an initial period, and after that they start releasing fire extinguishing chemicals like H2O and CO2. So this is the difference between the intumescent and passive barrier coatings. In our work, we have used the passive barrier coatings, and the reason simply is that the passive barrier coatings are much more suited for artificial leather. Artificial leather starts decomposing at a very much low temperature, and the temperature at which the intumescent coatings will release H2O and CO2 is never reached in case of artificial leather, be it PVC or polyurethane. So we have different sorts of material used as coatings. All nanoclays, montmorillonite, perlite, vermiculite are definitely used as for flame retardant coatings. Then we have the nitrogen containing organics like polyethylenimine, polydimethyldimethylammonium chloride, polyacrylamide are also used as fire retardant in coatings. Moving on, we have the well-known fire triangle or the fire tetrahedron here. We definitely require the oxygen, heat, and fuel to have the fire chemical chain reaction. Combustion of a polymer obviously is an exothermic process. Now, from the schematic shown here, our concerned region is this one. We have the initial heat of the fire, which leads to the thermal degradation, which leads to the generation of volatile products, which again which are again which are actually leading to flame, which again then generates the heat, and this cycle goes on. So if we try to have a coating at this phase boundary so that the volatile products generated, they never go outside, and the heat never comes inside, then our problem is solved. So this is where the flame retardant coatings act actually. They create a boundary. They themselves try to degrade, as in case of intumescent coatings, to release heat. They generate char, or they resist fire also in many cases. Moving on, so we have used layer by layer self-assembly in our case to coat the flame retardants. There are various other methods, but we have used the layer by layer assembly. As shown in the schematic here, suppose we have a substrate, then it is rinsed. Then it is first of all inserted in a negative. We have a substrate which is initially negatively charged, the surface. Then it is first of all inserted in a positively charged solution. Then it is rinsed and dried in water. Then again it is the negatively charged, then positively charged, then negatively. So there is like a buildup of negative, positive charges each over one, particles each over one another, giving to what we say here is a nano brick wall kind of structure. If you have to define the layer by layer assembly, it is basically the sequential process of alternate immersion of a charged substrate in aqueous solutions, alternately positive to negative. As shown in the figure here, we have a substrate, and then we have a one bilayer. One bilayer means one layer of the negative or positive, and other layer of the negative or positive. So we can see from the substrate here that the polymer is there. Then we have the nanomaterial, and the nanomaterial is attached in such a way over the polymer that it is giving some sort of a brick wall structure. And it is ideal actually to prevent the heat and oxygen going inside the substrate, and even the volatile materials coming out of the substrate, so that we can prevent fire. One point I would like to hear is that in our case, we have used PVC-based artificial leather because, as of now, the nano coatings have never been applied on PVC-based artificial leather to improve the fire retardant properties. Fillers have been added, different sort of fillers, antimony trioxide have been added, but none of the papers, none of the literature has not mentioned any sort of flame retardant nano coatings or coatings on the PVC based artificial leather. So this is the novelty of our work which we did. So coming on to the experimental part, we use simply the polydiallyl dimethyl ammonium chloride, PDDA, as we say, as a cationic layer, cationically charged polymer, and the montmorillonite nanoclay as the anionic layer. We have the structure here, PDDA. This is the PDDA. It is definitely negatively charged because of the presence, positively charged because of the presence of the the nitrogen. Then we have the montmorillonite structure here. Montmorillonite, as we can see that it has tetrahedron as an octahedral. The tetrahedron has silicon and silicon, oxygen and silicon bond, which is itself attached to the another tetrahedron having a silicon, oxygen, silicon bond, giving rise to an hexagonal structure. The other four corners of the tetrahedron are basically attached to the octahedron below, which has aluminum or magnesium, and even has the OH minus charges at the corners or the edges of the layer. So this presence of the OH minus is basically giving the negative charge to the montmorillonite nanoclay. In this figure, we can see the leather sample which I have used. This is the leather sample of a 30 centimeter length and 7.62 centimeter width. And then we have the 17 centimeter length and 7.62 centimeter wide leather sample, artificial leather sample. It was purchased from a local manufacturer in India. So the methodology is here. We have for both uncoated and coated leather, we tried coating. Like this is the uncoated leather. What we did with the uncoated leather is described here. we use the dip coating apparatus, which is shown in the next slide, coming slide. 13.5 centimeter into 7.6 centimeter of the the leather was coated. When we characterize using various techniques, SEM, FTIR, EDX, and we have the XRD also. And then we went to the when we tested the final tested it in the ultimate fire test, which is ASTM D6413 vertical frame test. We did the same for the coated leather, but a different thing was added here, which I will describe in the later part. First of all, we treated the coated leather with the corona treatment, namely corona discharge treater. We dipped it in the same coating using dip coating, same coating apparatus, but in this case only 17 centimeter on 7.6 centimeter of the fabric was coated. The reasons provided at the machine were not able, the equipment we have was not able to coat it. Although we were trying to, we did try to find out an alternative for that. We characterized the same. Then we have the ultimate test for the coated leather also. The table here is showing that the zeta potential of MMT and PDDA. We did this analysis just as to confirm whether the MMT is negatively charged and the PDDA is positively charged, which the given zeta potential values actually confirm. Moving on, so we are having the little description of the LBL process which we use. In the process, we use an amine salt called Tris buffer, which has been demonstrated to increase the coating uniformity. It has been noted in the literature that yes, the Tris buffer is actually able to build a more uniform nanobrick wall structure of the montmorillonite or other nanoclays like vermiculite. And it is widely believed that and mentioned in the literature that amine salts like Tris buffer, they interact very strongly with the negatively charged nanoclay and nanoclay platelets, leading to a better nanobrick wall structure. The following dipping systems was followed. We have the aqueous solution of PDDA 1 weight % plus Tris buffer 50 molar at a pH of 6. Tris buffer again in the other beaker solution of 50 millimolar at pH 6. Then we have the aqueous montmorillonite solution 1 weight % at a pH of 10. Then we simply had the water at pH of 10. In this study, 6, 12, and 20 bilayers were coated on different samples. So as I was talking about the dip coating apparatus, here we have the dip coating apparatus. It was an Apex dip coating apparatus purchased from a local manufacturer in India. We had the different sort of coding here. We did the coding and the apparatus actually coated the samples accordingly as per our coding. Then, as I was talking about the corona treatment, which I am giving a glimpse here, we can see from here that this is the electrode and this is the discharge. The discharge is basically the electric breakdown of air, which is happening because of the high potential developed by the electrode, and the effects on its surface I am going to discuss later. So, coming to the characterization, we have the scanning electron microscopy. The two images are quite quite different. We have the market uncoated or control leather. We can exactly see from the surface that yes, there is a coating on the coating deposited on the coated leather, and the uncoated leather is simply clean. There is nothing on it. Coming to we also did the thermogravimetric analysis so as to confirm the coating. I'd like to say here that most of the characterization techniques here we did was to confirm the coating. So here also we have the coated and the non-coated leather, and we can easily see that yes, at around 800 degrees Celsius or between 600, we have more coated. The charge and developed by the coated leather is much more compared to the charge developed by the non-coated leather. It actually confirms that yes, we have a coating on the coated the leather which we coated compared to the leather which we didn't coat. Moving on to the X-ray diffraction, at around 21 degrees, we have the peak of the coated leather matching with those of the MMT, and also at around 27 degrees, which also again confirmed the presence of montmorillonite in the coating. attenuated total reflectance Fourier transform infrared spectroscopy studies were also done. So we have a peak of at around 900 centimeter inverse, which actually represents the silicon oxygen silicon bond stretching in the in the in the nanoclay. In the nanoclay, which actually confirms that yes, we had the nanoclay deposited. Then we have the peak at around 1400 centimeter inverse, which actually confirms the methyl group deformation due to tertiary and quaternary amines. These two things were confirmed by the these two results, these two observations were actually confirmed with the literature. Then we have the energy dispersive X-ray analysis. We have the coated leather and the market leather, or we can say the uncoated or the control leather. In the coated leather, we can simply say we have the presence of nitrogen. We have a substantial peak of oxygen and a very much high quantity of silicon. So we have silicon, which confirms the presence of MMT. Then we have oxygen, which also confirms the presence of MMT. And then again, we have the nitrogen, which again confirms the presence of polydihalide dimethyl ammonium chloride. Coming to the market leather or uncoated leather, we do not have any peak of silicon, which says we have a peak of silicon, but that is compared to the coated leather, which is very small, and it gives an inference that yes, the coated leather was actually having a nanoclay coating, but the market leather, the uncoated leather, was not having the coating. It was simply having silicon, which could be present as which was present as a filler inside the artificial leather. And the market leather doesn't have any nitrogen peaks, giving the inference that it wasn't having any PDDA coating. PDDA is in the coating. So coming to the ultimate test which we did, we have the ASTM D6413 vertical film test apparatus. This we designed locally in our lab. It was designed by myself. I only designed it according to the ASTM standards. I will give a brief about the ASTM standards here. So the standards basically say that we should have a 30.5 into around 7.5 or more than 7.5 width wide fabric, which has to be exposed to a flame for 12 seconds, and the length of the flame should be 1.5 inches. So, and it has to be done in a closed chamber so that no hazard or no toxic fumes come out. We followed the exact same procedure. The 12 seconds, the timer was maintained here. I will actually play the video here. Yeah. So this is basically for the uncoated leather. I hope the video is clear. As you can see, the flame was exactly removed after 12 seconds. I will not, I'm very sorry, but I'll be unable to play the complete video, but I can, because of the paucity of the time here, but I can definitely say that this fabric burned for more than 2 minutes, which is a substantial time, and it can lead to the propagation of spread of fire. We can see the fabric length, the destroyed fabric here also in the image. So this is the vertical flame test for the coated equipment, coated fabric. I am not writing here the ASTM D6443 standard because the fabric actually we were unable to meet the standards as we were unable to meet the standards because the 17 centimeter length the 30 centimeter length was not met because of the complications with our machine, the limitations with our dip coating machine. We can see that we have the coating here and we have the coating here on the back side, and after the test we have the complete fabric is not destroyed, the fabric is left. The fire was extinguished only in 20 seconds. I will just play the video. the fabric was extinguished just in 20 seconds, as I mentioned here. So after that, we also have the corona treatment studies. We have the corona discharge. So we did the corona treatment studies so as to achieve high polarity on the polymer surfaces. It is mentioned and researched thoroughly in the literature that yes, the plasma formed due to the corona discharge actually reacts with the surface of any sort of polymer and leads to the breakage of CH bond to form a polar carbonyl and carboxyl groups, which are actually negatively charged, giving a negative charge on the surface. So it also noted that a too intensive treatment might cause a weak bond strength between surface substrate and coating. It might lead to the destruction or the burning of the coating substrate. So we had the corona discharge only for 20 seconds. Then we did the contact angle treatment, so that we can identify, so that we can get a hint that yes, a negative charge has been developed on the surface. Contact angle treatment was done in this way. I will explain in the next slide. So we have the graph here, we have the plots here. We can say that yes, for the MMT treated, we have the treated leather treated with the corona treater, and MMT was poured on it. MMT drop was poured on it using the contact angle measurement. We can say that it is making a very large angle at around 57 degrees. And when we have the MMT drop poured on the untreated leather also, it is making the same angle. So we can definitely say that yes, earlier also the surface was having a negatively charged, and after the treatment also the surface was having a negative charge. So that the MMT, which is already negative charge, those two are repelling each other and the drop is not actually spreading. But then we have the polydiol PDDA, which is actually positive charge polymer on the untreated surface. It actually spreads a bit, not much. A degree of 50 degrees was made, much better than the MMT. But when the treated leather the PDDA was poured during the contact angle measurement, we had an angle of around 25 degrees, it spread a lot. It actually confirms that yes, it is spreading because we have negatively charged developed because of the corona treatment. I would like to say here that yes, it actually gives a hint of the surface charge developed, but we were not sure that it is actually confirming our hypothesis that yes, negative charge has been developed on the surface because of corona treatment. We have the results here. The characterization techniques have confirmed the coating. Contact angle results definitely hinted that yes, negative charge was developed because of the corona treatment. We have the 6, 10, and 12 bilayers. They all failed in the vertical flame test result. But when it came to the 20 bilayers, it passed as I shown in the previous slides. It burned only for 21 seconds and only 11 centimeter out of the 17 centimeter fabric was burned. Conclusion: the 17 centimeter the coated leather with 20 bilayers, it actually exhibited a very remarkable, very outstanding fire retardant properties. We concluded that yes, a proper uniform nanobrick wall structure was developed. We also like to know that as I mentioned earlier, our study was having certain limitations, such as the smaller length of the leather, which we were required to we have the smaller length, but a larger length of leather was required to satisfy the ASTM DCC 413 vertical flame test. We also noted that yes, the coated leather samples with bilayers less than 20, although they didn't exhibited any sort of flame retardant properties, but they did resist the fire, as evident that with the increased number of bilayers, the burning time decreased. So as the burning time is decreasing, it means that more char was developed, and the char was actually trying to extinguish the fire. We also like to know that yes, more optimization is required, as we were unable to measure the thickness of the coating. It was one of our planned thing that we will measure the thickness, but we were unable to do that because of the paucity of time because of the corona pandemic. We plan to test more samples, but we were again unable to do so because of the paucity of time. Effect of the pH of the dipping solutions, various corona treatment time. We plan to change the corona treatment time from 20 to 30 or to 1 minute. Although I would like to mention that the task mentioned here, which we were unable to accomplish, will be accomplished further by my co-workers and my supervisor in future. So we have the team. I'm here. I just completed my master's in chemical engineering from BITS Pilani in June 2021. we have my co-worker was the PhD candidate in BITS Pilani, and this is my supervisor, Dr. Krishna Yatika. He is an assistant professor in Department of Chemical Engineering, BITS Pilani. So thank you very much. Thank you, the organizing committee, and thank you, Mr. Nawaz, for giving me this opportunity. Thank you all. These are the references. Thank you. I'm open for questions.
Thank you so much, Akshat Verma. Thank you for the excellent presentation. Yes, we're open for questions. If any questions? Any questions for Akshat Verma?
I think I have two questions.
Thanks very much,
Yes,
Dr.
please.
Akshat, for a nice presentation.
Thank you. Thank you.
Yes, Dr. Lotham, please.
Okay, so thank you for a very interesting presentation, Akshat. I liked it very much. You have most definitely put in a lot of energy and a lot of effort, a lot of work into this. I have two simple questions of a maybe more basic nature. First of all, the corona treatment in order to increase the higher polarity on the polymeric surfaces, that I'm familiar with this, of course, and that is also the reason why I'm sort of curious about alternative methods. Just a very general question. If you don't want to use corona treatment for whatever reason, what other alternative method would you choose in order to increase polarity of the polymeric surfaces? And the second question that I have is about the contact angle. I assume that you were measuring a static contact angle. Did you try also to measure dynamic, as well as did you see, if so, did you see a difference between receding and advancing contact angle, right? I'm just curious, maybe one would get more information about the nature of the surface itself in that respect. Yeah, thank you again very much for your really interesting presentation. And yeah, those were my questions.
Yes, sir. Yeah. First of all, thank you, Dr. Paul Ockman. So, as per your question, that what alternative methods can be used if you're not willing to use the corona treater? Sir, I would like to note it here that in the beginning of my dissertation, for the first 4 months, I was not having the corona treater. So, it came only in the month of October last year. 2020. So for the first 2 months, we did try to coat the surface using alternative methods instead of the corona treatment. First of all, what I did was, we had the conditioning of leather in water for around overnight. What we hypothesized was that the OH minus ions, OH minus ions present in the water, they will try to deposit on the leather surface overnight or for a more duration, and it will give a very feeble polarity, increase than what we have if we are not conditioning it, but we will give a very feeble polarity but an increased polarity on the surface. So this is the one which I followed. The other one, we can also use other solutions which I'm not aware of basically, but I believe that yes, there are other more solutions in which the leather surface can be conditioned, so for overnight or for more duration, so that we have a much more polarity developed on the surface. But we need to take care of that. The other solutions which we'll be using for developing polarity, they may degrade the surface also. So for your other question, yeah, so as you said that did we perform the dynamic contact angle measurement or not? So we didn't. We did plan to do it, and in our future, I believe that my supervisor there, Dr. Krishna Yatika, and the research scholar, he will try it, but we were not able to do it because of the paucity of time, because of the corona pandemic. Yeah, sir. That is the reason. Actually, my dissertation was stopped in the month of March itself, although it was planned till May.
Okay. Yeah, I just thought that, in general terms, when it comes to surface characterizations using this different kinds of measuring methods and interpretation of the contact angle by dynamic as well as receding and advancing will actually
yes.
give quite a lot more information about the nature of the surface. Yeah, thank you so much. That was a great presentation again, and thank you for your wonderful answers.
Thank you, Dr. Lathan.
Yes, any more questions? Okay. Okay, thank you so much, Akshat. It was
Thank you.
a nice presentation. Thank you very much. Our next speaker for today is Professor J.C. Umavati from Gulbarga University, India. And I request Professor Umavati to start her presentation.
Yes.
Yes, our next speaker is Anatoly Zardavin from Pervyaz of Ukraine, and he's going to give a presentation on application of the PAGMAW in wire arc additive manufacturing. And I request Anatoly to start his presentation.
Yes, I have shared my presentation. Is
Yes,
it visible?
Yes, it is visible. Please continue.
Thank you very much. So let me start, and just a second. Yeah. Thank you for your kind introduction of my presentation, and the title is Application of the Pulse Arc Gas Metal Arc Welding in Wire Arc Additive Manufacturing. So wire arc additive manufacturing is layer by layer construction of some details. For example, in a very simple way is modeling of wall, and it will be multi-layer deposition of metal. But first step in this procedure is the first deposited layer, and here we can see weldment, and it characterized by some parameters, exactly seam widths, penetration depths, and heat affected zone. These parameters are very important in any welding procedure, and especially in wire arc additive manufacturing. So to improve the whole process of wire arc additive manufacturing, usually used a new progressive welding source, and something like this. Here we have welding source Phoenix 501 equipped with pulsed equipment. And what does it mean, pulse arc welding? It means that we have complex characteristics of welding current, and here we have pulse zone and pulse zone. And such innovation and such improvement gives opportunity to govern of whole welding process. But if we have parameters of pulse current, current of pulse, frequency of pulses, and duty cycle, we have 4 independent parameters. And if we use several levels of these each parameters, for example, low, medium, and high, we have possible 81 experimental trials. But it is very expensive to choose each of experiment, and in this connection, there is a design of experiment methods, Taguchi algorithm. This algorithm gives opportunity to calculate from 9 separated weldments the whole 81 experiments. So we have for this procedure following regimes or following modes. For pulse current, we choose value from 160 to 240. And for base current, the welding current from 80 to 140. For frequency, we choose low frequency from 0.5 to 5 Hertz. And for duty cycle, as usual, we choose from 40% to 80%. This is most common duty cycles. And here we can see 9 weldments. And this is a general view of welds. And here we can see a general view of cross sections of weldments. So we can see that there is a different penetration depths and there is a different seam welds and as well as heat affected zone. But for wire arc additive manufacturing, we have to choose from these all trails the most favorable. For example, after calculation of all data, we got the input of each parameter to formation, for example, on penetration depths or seam widths, as well as percentage of each parameter input. Based on this data, we propose the optimal regimes or optimal welding modes for further investigation. For example, we have chosen the mode which possesses minimum penetration depth. So when we have made experimental trials, we established that our calculation well correlate with experiment. So for further investigation, we choose the mode which gives minimum penetration depth. And here we create a model wall consists from five layers deposition. Here we can see one wall and second wall. We have made, first of all, our calculated welding mode, and the second one is standard regime. And for this and for these modes, we use the equal average current, welding current. So we can see that developed welding mode gives more sound formation of weldments, more sharp edge of model wall, and as well as we have more fine grain structure. Here represented delta ferrite grains of austenitic welded material. And one of important things is the homogeneity of chemical composition distribution from layer to layer. Here represented distribution of chemical compositions from 1 to 5th layer. The most interesting is the 3rd, 4th, and 5th layers. This is rounded by second layer have threshold, which is caused by influence of substrate. And second one represent mixing of previous one layer. So the representative layers of model wall will be 3rd, 4th, and 5th layers. And as we can see, the chemical composition is quite uniform. And we have the following advantages of such welding mode and formed structure in mechanical properties. Here presented the distribution of microhardness from each level or each layer. And as we can see, the pulse arc gas metal arc welding development welding mode gives a more high value of hardness, and the deviation of values is lower than for pulse current gas metal arc welding. Thus, we can state the following conclusions. Application of the pulse arc gas metal arc welding based on optimal parameters is more favorable for wire arc additive manufacturing. And we have the following advantages. First of all, sound formation of the welds. Second one is chemical composition homogeneity. And third one, mechanical properties much higher than for standard mode. Thank you for your attention, and please your questions. I am ready to hear any question. Have you?
Yes, thank you so much, Anatoly.
Thank you very much for your attention. I'm glad to hear questions.
Any questions for Anatoly?
If any, you can write me on email, and I available anytime. With pleasure.
Yes. Yes. Thank you so much. Thank you for.
Thank you very much for your attention. Thank you.
Have you shared?
Yes, I have
My
shared.
screen you have shared?
I have shared the PPT laptop. You can present from here.
Give again a talk on using the nano materials in coatings. So this is my application area. Before going for what is nanotechnology, just a glimpse of nanotechnology. Nanotechnology is used in engineering DNAs and buckyballs, and also in semiconducting metals. Since yesterday, we are hearing talks on application areas of nanomaterials, preparation of nanomaterials. And just now, the last but one talk was on coatings using nanomaterials, and also a recent application with Corona, this one. And also we have heard about the application of nanomaterials in bacteria generation, and also in taking gold nanoparticles, discs. So many classes we have attended. Just a few glimpses of, again, few more applications of nano technologies in cancer treatment. As we know that the cancer treatment is possible when it is detected in the early stage. The patient will be getting cured. So in early times, the technology in medicine was not so advanced. So knowing whether the patient is a cancer patient or not, we have to take only the scanning, and then these tests would have been advanced stage. So by now using the nanotechnology, we can detect in the body very early which part of the body is affected with cancer. And also gold nanoparticles are being used. How the gold nanoparticles are being used is wherever which part of the body is affected with cancer, they are going to because they have to remove the bad cells and improve the good cells. So what they are going to do is, on that part, they are going to pack with the gold nanoparticles, so that what is going to happen is these bad cells will not get multiplied and affect and increase the cancer growth. So in India, in Bangalore, this one is very successful. Using gold nanoparticles, the patient has got curing and he is back to normal. So just I wanted to share this with you. And also in agriculture, how in agriculture the nanotechnology is used means, sensors. Through sensors, actually, whenever you have some encapsulation, we tell. This part was also discussed in the earlier talks. Encapsulation means what is going to happen here is, if you have a tree or a plant affected, so now the process of removing those germs on the plants is we spray. So we spray a chemical on the whole plant. The problem with this, what is going to happen is the spray goes with on the living flowers also, and that flower will intake the chemicals. So our food becomes a bit poisonous, though we don't feel it, but it is true. So in order to avoid, so that's why nowadays we are going for Green Go, wherein we don't use any pesticides for the plantation. Of course, the cost is too high when you compare with these things. What I mean to say is, in order to avoid these types of spreading of the chemicals on the plant, using the nanotechnology, they encapsulate the medicine inside, and what is going to happen is that medicine will be released for only the part of the plant where it is affected, so that the other part of the plant will not be chemically destroyed. Also in aeronautics and also in space launching, you have ample of, even in computer chips, we are using nanomaterials. So when you use in the SIM that chips, using, they coat it, the same chip, they coat it, but gold is found to be the best transportation, but of course the cost is more here. But and also the shape, while preparing these nano coatings, the shape of the chip is converted into a shape of the butterfly, because in nature we know that butterfly will have the instead of a rectangle or a square, it is not yet coming to the market, but research work is going on, changing the shape of the chip also in the form of a butterfly shape, and then coating with the gold nanoparticles. That is also, and also in real world applications, if you talk in terms of say for example fridge, you can give a lot of talks on the application, but just I wanted to give the glimpses. So nowadays we are having hair company have already launched a fridge wherein they will have inside different motors which will control the temperature on that particular place, which is very costly. So instead of that, you have only one motor in the fridge, and have the bowls. Using these bowls, which are made up of nanomaterials, you can control the temperature. So for example, if you keep leaves, it does not require more cooling. It will get soon wasted. So in order to, depending on the temperature of the material, resistance temperature of the material, and you can go for long say this one storage using these what we call it as dishes prepared with nanomaterials, which will automatically control the temperature of the material which is kept inside. That is also one of the very important. So in view of this, I just want to start my actual work. The title of my work is basically, I am a pure mathematician. So my analysis is only theoretical modeling. Of course, we have application comparisons also. So here, the computation of von Karman thermosoluted swirling flow
of a nanofluid over a rotating disk to a non-Darcian porous medium with hydrodynamic thermal slip. Yesterday we have attended one beautiful talk. You have observed while coating they used the disk shape, rotating disk shape in the preparation of nanomaterials and in coatings. So this is very much applicable to such experiments. As I already told, the important application of this topic is with coatings, that too with spinning. You can coat the material while it is spinning. That is the importance. Normally, we see papers with only a geometry, either a disc or a cylinder, but it is not spinning. But this is the paper contributed particularly during spinning, how we have to go for coatings and how we have to implement mathematically. So before going for the mathematical modeling, as we know that nanofluids, it's a biased one regarding its modeling. Few people argue that it is a two-phase model, and few people argue that it is a homogeneous one fluid model. So yesterday while preparing nanoparticles, that's what we had the discussion, whether to consider two-phase model or one phase model. It is still a biased one. So here I'm also working on taking the same formulation approach with two different models and see what is the difference. Of course, when we consider the slip effects, considering Buongiorno's and considering Tiwari, we are getting different results. So it is still a biased one, and there is no any experimental proof that which model we have to consider. Only we are just approaching it through mathematics. Some researchers consider two fluids, some researchers consider one fluid, but still this is a big question mark for the researchers. Okay, that is one part. Here I am considering two fluid model, that is Buongiorno's model. So the geometry is, as I have already told, we are studying heat and mass transfer in a swirling slip flow of a nanofluid from a rotating disk, which is homogeneous, and it is immersed in the porous medium. So the thermophoresis, the Brownian movement of nanoparticles, the Buongiorno's nanoscale model. All these things. Are you hearing me?
Yes. Please continue.
Okay. Okay. So this is all about the introduction. Those things I'm not going to deal in detail. That is the citations and related material. I just wanted to show some of the geometry and what are the slip conditions I have considered. Navas, can you scroll down? I'm unable to scroll. Okay. Yeah. Please go to page number 9. Page number 9.
Okay.
9.
Okay.
Yeah. This is the geometry that I have considered. A rotating disk. Omega is the angular rotation, and we are considering the nanoscale particles. V, U, W. I is your angle between the Y and the W direction. R is your radial velocity. And next, what are the boundary conditions we have to consider? Please scroll here in the same page. We have equation 2.7
this is very important. This is the main contribution of my work. Here I am considering no slip conditions. So U is L1 dou U by dou Z, V is L1 dou U by dou Z plus R omega, W is 0, T is TW plus L2 dou T by. These L1, L2 are our slip parameters. Okay, and these are the transformations. I'm not going in detail about the transformations, just I have provided equation number 2.9 to 2.12. So who are working in the fluid mechanics, the first one is your equation of motion. The second one is your radial and angular velocities, energy equation. The last one is your solid volume fraction equation, which is the contribution for the presence of nanoparticles. So the non-dimensional boundary conditions are given in equations 2.13 and 2.14. I just give you the bit introduction about the non-dimensional parameters. Equation number 2.15, where I is your inertial parameter. I'm including the inertial parameter also, along with the Darcy parameter. Sigma is your Darcy, RE is your Reynolds, NB, NT, they are all for the nanoparticle dimensionless numbers. If NB, NT equals to 0, you get your regular fluid. So we can get back with this calculation. The beauty of this calculation is if you just put in the equations NB, NT 0, we get the pure fluid. So that can also be used while coatings. Schemick number, Prandtl number, and here you have thermal diffusivity. Then equation 2.18 is the important equation, because this will give you the numerical values of how much is the heat transfer, Nusselt values at the ends of the disk. Then equation 3.1, coming to equation 3.1. As we know that the basic equations are nonlinear, hence it's not possible to find the closed form solutions. Anyhow, we have to go for the numerical methods. As we know very well that in MATLAB, the well-known Runge-Kutta shooting method, already program is there. We need not bother about its convergency and all those things. It is a ready-made package. So we directly use this BVP4C. But what we have done in order to have whether the results are comparative analysis, we have to do. It's not just taking the equations, fit in, and then run the program. It's not that way. Anyhow, we have to validate through at least one of the other numerical method. What we have done in this one is we have modified the Runge-Kutta fourth order formula in the mid and redefine that to be in the form of y1 plus, which is given in equation 3.1. This is also one of the contribution which is already verified with Udine et al. So using Runge-Kutta, here we have modified the formula. Instead of in the regular formula, we have K1 plus K2 by 4, K3 by 6, K4. Instead of that, we have used 3.1. And we have also used the well-known Adams-Moulton predictor corrector formula to validate our results. So equation 4.1, 4.2, 4.3, and 4.4 gives you the functions converted into first order ODE and the grid generations, that is Adams-Moulton. Using two-step predictor relations, we rewrite the grid generation, that is the relation between it is an iterative scheme. So we have to have a relation between K and K plus 1 nodes. So corresponding, this is your 4.5 to 4.8 is your predictor, and 4.9 to 4.12 is your corrector. So I have given in table 1, that is page number 14, table 1. This will give you a clear picture of the BUP4C, which is using MATLAB and Adam Moulton predictor corrector method. So you can see it is almost equal. Actually, I have taken BUP4C up to 8 decimal accuracy. That means the error will be 10 raised minus 9 up to 8 decimal accuracy I have taken. So when on the boundary at 0, the values are equal between BUP4C and the MPC, but when you go for inside the disk, you have a bit difference, but not very much. It is almost similar up to 6 decimal places. That is enough for us. We are not doing any sensitive analysis here. Just comparing whether our results are correct or not. It's enough if we get even 4 to 5 decimal comparison analysis. And also I have given regarding the temperature, just for our justification, yes, our results are correct. So page number, next we go for analyzation with the different parameters. Page number 16, graphs. Please go to page number 16, graphs. So here figure 2 represents your radial velocity for distinct values of gamma. As you can see, 0 to infinity. My geometry is from 0 to infinity. So here, if your BUP4C is convergent, infinity, anyhow, we have to fix. Infinity in mathematics is not infinity. It is a value where it is large when compared to 0. Say for example, again, this we have to do. This we have to check the program for what values of infinity. I have to give numerical values. Some programs take 7, 8, 10, depends on the matrix convergency. So for this problem, I got convergency if I take even 7 up to 7. That means infinity value is fixed to be 7. How we can justify is you can see in the graph. After 4, eta, after 4, all the curves they merge and they will be linear. Linear in the sense there will, that counts for your convergency. That's all. Okay. So in the boundary layer, because it's a boundary layer problem, so here you can see that the effect of gamma is as gamma increases, the radial velocity decreases. Next, figure number 3. Here, tangential velocity. Here also we are going to have the similar nature, that both whether radial velocity or tangential velocity, it is going to reduce the velocity in total. And effect of sigma, which is porous parameter, as we know very well that whenever you have a fluid with porous bed and without porous bed, because of porous beads, naturally the velocity will be reduced. Similar nature, whether you include nanoparticles or not, but one should be very careful when we consider the porous bed in using nanoparticles. One should be very careful, because this porous bed should not stop the nanomaterials. The void space should be more when we consider the porous matrix. It is good if you have more void space, so that the clogging of nanoparticles cannot be faced. That is that part one should be. When we are doing mathematical analysis, we don't find any difficulty, because the analysis will take care of us. But when we enter into experiments, one should be very careful. So as you know, porous matrix beads, if the void space is more, velocity is more. If the void space is less, velocity will be less. So that's the reason why velocity decreases as the porosity increases. This is a standard results one normally gets even with regular fluids also. Similar result even for the nanoparticle, nanofluids also. But that's what I told. When you take the experiment, one should be very careful how to fix the value of porosity. or what should be the value of porosity. So axial velocity also decreases. Figure 6, tangential velocity. Yeah, here figure number 6. Nawaz, figure number 6. Yeah. Here you observe that in the tangential velocity, there is a change. What is going to happen is near the boundary, that is at theta equals to 0, it is going to have the usual classical result that as sigma increases, the velocity decreases. But this is a tangential velocity. So what when we are taking, because of rotation, that's the reason during spinning the properties will change rather than having the geometry fixed. So the tangential velocity is reversed. It is reversed, say for example, approximately at theta equals to 2.5. But near the boundary, it satisfies the classical result. So because of rotation, these are the results that we have obtained. And figure number 7, that is tangential velocity for inertial. Inertial does not depend on the spin, because inertia is related with the porous bed, and it is a drag force caused due to the porous matrix. So here we don't find any difference. That is again we are getting the classical result only. Any drag resists the velocity, whether it is radial velocity or tangential velocity. So that's what I told. Figure 7 and 8, figure 8, both radial velocity and tangential velocity is to suppress the velocity. And also here we are having temperature, that is figure number 10. Now let's go to figure number 10. Okay. So figure number 10, here it is the chart that we have prepared, including the effects of Prandtl number. Prandtl number is an important because it characterizes what type of fluid we are going to consider. So small Prandtl number, large Prandtl number, I will not go into its physics. Just Prandtl, by seeing the Prandtl number, we can choose which appropriate fluid we have to consider depending on the experiment. So here you observe that the temperature for porous parameter, when we consider Prandtl number, whether 7 or 5, doesn't matter. Whatever may be the Prandtl number, 7 is for water, 6.8 is for water, but I have taken 7, so less than Prandtl number. So that doesn't matter. Of course, I have not considered less than 1 Prandtl number because I did not get convergency. So here, that's the problem. Whenever we use any of the ready-made packages, so we can't change the program. So we have to restrict our values. If it is not convergent, we have to drop that value. But when we write our own code, we can make, but the researchers nowadays, the students are all interested in ready-made packages. So these are the difficulties that we face when we use the ready-made packages. So I could not run my code when Prandtl number is less than 1. Matrix convergency was not there. So whether 5 or 7, but interesting thing is as sigma increases, temperature also. I have not included in the temperature equation any of the Darcy dissipation. Actually, in fact, when we discuss dissipation and Darcy dissipations, that will play a major role. But I have not included both the viscous dissipation and Darcy dissipations. If we include, these dissipations will hinder the temperature distribution. But since the problem is related to coatings, so that will not matter a lot. Only numerically it will change, but that contribution is not. Normally, whenever we go for practical implementations, these dissipations does not really change the results. Numerically, when we analyze the things, that is different part, but not major contribution, these dissipations. So that's the reason why I am stressing. Normally, even temperature also should reduce, but I have not considered the viscous and Darcy dissipations. So the sigma is going to improve conductivity because of the presence of nanoparticles. And here also temperature for distinct I, that is Prandtl number. When we consider the temperature, inertial drag also helps to improve the temperature. And NT and NB, they are also helpful because of the presence of nanoparticles. Thermal diffusivity. So thermal diffusivity, you know, it is a diffusivity, so it helps to reduce. Diffuses. It diffuses means it reduces. Similarly, figure number 14, concentration. This is important. What is the meaning of concentration here is how much we are adding the nanoparticles. So as phi increases, that means we are taking more concentration. That means we are mixing more nanoparticles in the base fluid. So phi contributes for your concentration. Then inertia, then we have a Schmidt number, then figure number 17, figure number 18, concentration for distinct alpha. So actually I have already submitted this paper, so shortly it will revised form. So for in more details you can refer after it is published. Next I will conclude. The conclusions is a theoretical and computational study of the steady heat and mass transfer in von Karman Sperling slip flow of a nanofluid from a rotating disk adjacent to a homogeneous non-Darcy porous medium has been presented. Porous medium is Darcy-Forchheimer-Brinkmann model. Thermophoresis and Brownian dynamics, that is Buongiorno's model. Then von Karman similarity variables are deployed to convert PDE into ODE. This is the normal steps that any researcher will do while solving the problem, as I have already explained, converting the PDEs into ODEs and then ODEs into one-dimensional, that is one-dimensional ODEs. This is a technique that we apply when we use Runge-Kutta shooting method and directly use the MATLAB. But also we have compared with the predictor formula for the validity of our results. So the conclusions are page number 28. Point 1, radial, axial and tangential velocities are reduced, increasing the inertial drag, which is a classical result again. And what happens with the slip? That is very important. That is my contribution. Hydrodynamic wall slip, whereas they are elevated with increasing permeability. So if you increase the permeability, wall slip hydrodynamics values are also increased. Thermal and nanoparticle concentration boundary layers are also markedly modified with increasing Forchheimer, Prandtl, Schmidt, Brownian, and thermophoresis. That means the nanoparticle concentration boundary layers are countable when we use the nanofluid. And nanoparticle boundary layer thickness is therefore also reduced with stronger thermal slip boundary. This is very, 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 very important result, because when we apply for coatings, the boundary layer thickness should be as small as possible. So using nanoparticles, it's a good result. Using nanoparticles, the boundary layer thickness is reduced. So that's why it is more good or it is valid if we include nanoparticles in the coating problems or coating applications. Then species diffusion of nanoparticles it deaccelerates with nanoparticle boundary layer thickness. So diffusion is reduced in the presence of nanoparticles, and increasing permeability parameter, thermal conduction is boosted, and this results in the elevation in nanofluid temperatures. And increment in Forchheimer inertial also strongly elevate temperatures, and this is very important, because whenever you have augmentation or energy conservation, this temperature should increase. So this is a good trend that including the porous matrix Forchheimer inertial drag parameter helps to elevate the temperature. And then radial velocity, axial velocity are suppressed with increasing the inertial parameter. And as I told, Von Karman flow in nanofluid saturated porous media adjacent to a rotating disk of relevance to nanomaterial spin coatings. This is particularly spin coatings. So the analysis has been confined to steady state. Of course, we have to include the surface tension. I have not included the surface tension and chemical reaction effects that were yet to be included, because in coatings we also use different types of chemicals. Just one participant presented about the coatings. I will not go in detail. So yet that has to be studied. And in practical spin coatings, the viscosity of the nanofluid and surface tension results in elevating the thickness of the film. And baking at high temperatures and spinning process causes the removal of the solvent. This is also very important. When you are instead of keeping the disk constant and coating, and making spinning and coating has a lot of difference. So if you have spinning, you can remove the solvent very easily, of course with high temperature. But for coatings, it is better to have a spinning so that it coats equally, and the temperature with high temperature. Again, what is the temperature? It depends on the coating material and the nanoparticle material. Of course, we can also go for non-Newtonian nanofluid aspects in future work. So I thank Nawaz for giving me this job instantly. So I could not prepare well. I don't know how far I could reach the participants, but something I tried. So questions are welcome.
Thank you so much, Professor Mauti. It was so nice of you to accept the request and present now. Thank you so much.
Okay.
Any questions for Professor Mauti? Our next presenter is Dr. Olga Shikimaka from Institute of Applied Physics, Moldova, and she is going to give a presentation on main factors influencing the relaxation process under micro and nano indentation. And I request Dr. Olga to start her presentation.
Thank you. Do you hear me?
Yes.
And,
yes.
Okay. Do you see my presentation?
Yes, yes, yes. Please continue.
Okay, okay. And full screen is okay.
Yes.
First of all, I would like to thank very much the organizer of this wonderful event, so that bring together and bridge scientists from all over the world in dealing with material science and engineering. And I would like to thank for invitation. It's my pleasure to take part in this very interesting, really, and useful events. And let me please to begin my presentation. I am Olga Shikimaka, the head of Laboratory of Mechanical Properties of Materials, Institute of Applied Physics, Moldova. And the title of my presentation is Main Factors Influencing the Relaxation Processes under Micro and Nano Indentation. The outline of my presentation, introduction, then I will speak about phases of stress relaxation under micro and nano indentation, then about the mechanism of deformation for the dissipation of the induced internal stresses, and then I will speak about the factors influencing the relaxation processes, and namely the structure, strain rate and load, time-dependent factors, temperature of deformation, and finally conclusions. The nano-indentation and micro-indentation methods are the main one for mechanical characterization of size-limited materials like thin films, fibers, nanocrystals, nanocomposites, etc., from very soft biological objects to super hard ceramics. The study of the mechanism of deformation under nano-indentation and micro-indentation remain the topics of great interest for understanding the reason of specific deformation of various materials as a function of structure, composition, and load conditions, with the end aim designing materials with desired mechanical properties. The indentation process induces a very non-uniform stress strain field, where the stresses decrease inverse proportionally with the square distance from the applied load, and as a result, very strong gradient of plastic and elastic deformation is created around the indentation. And here one can see the main zones created under beneath the indentation, and the close vicinity is the zone of hydrostatic compression, then this zone of strong gradient of plastic strain, beneath which the elastoplastic deformation zone, and which is surrounded by elastic deformation zone. What of this zone will be developed for any materials depends on the specific behavior of material and the possibility to dissipate the external mechanical energy into the inherent for the relaxation of the induced inherent stresses. And the relaxation of the induced stresses begins just at the loading, when the indenture penetrates the material, and the dissipation of stored elastic energy begins into the irreversible plastic deformation. And for brittle material, the initial stages of fracture also can take place at this stage. The next stage continue the relaxation during holding under the maximum load, where for some material the grip may be developed. Then the relaxation continue during the unloading, and this is an active relaxation phase when the elastic recovery of indentation and the restructuring of the plastic zone take place, and the crack growth and fracture development for brittle materials. And finally, the last relaxation phase set in after full load release. The relaxation of the stored elastic energy and the dissipation of this stored elastic energy can take place through different channels, i.e. mechanism of deformation such as dislocation, translation plasticity, phase transition, rotation plasticity, interstitial plasticity, fracture, and for vitreous materials, the permanent densification, and the special mode of plastic flow. And which of these mechanisms will be developed depend on many factors. And first of all, depend on the structure of material: crystalline, polycrystalline, nanocrystalline, composite, vitreous, including type of atomic bond, ionic, covalent, metallic, van der Waals, and crystalline lattice structure. And here I would like to present some specific mechanism of deformation. For example, for crystalline and polycrystalline materials with ionic and metallic type of bonds, the dislocation, translation, plasticity is characteristics. For covalent crystals like silicon or germanium with poor dislocation mobility, the phase transition and fracture is developed. The rotation plasticity disclination mechanism is characteristic for nanocrystalline and polycrystalline intergranular materials. Then the vitreous materials, as I say, has a permanent densification and special mode of plastic flow as a deformation mechanism. And for materials with poor developed plastic deformation or at high strain levels, the fracture is developed. And next, I would like to present some examples of this mechanism or relaxation processes. And here you can see the dislocation rosets around the indentation Vickers and Berkovich indentation revealed by the HP technique. And I would like to show you that what presents the Vickers and the Berkovich indentures. These are the diamond pyramids. Vickers is the tetrahedral and Berkovich trihedral with the apical angle of 68 between axis and face for Vickers and 65.3 for Berkovich. Next, as well, an example of phase transition under non-indentation of silicon single crystals. It is well known that silicon under high pressure and especially during indentation undergoes a series of phase transformation, and namely from diamond cubic silicon 1 to beta stam silicon 2 structure, and then to base cubic silicon 3, rhombohedral silicon 12, or amorphous silicon, depending on the unloading rate. And here one can see a cross-section or a TEM image of the cross-section of a spherical indentation of silicon. And you can see here the zone B is a base-centered cubic structure. The rotation plasticity, as I say, is developed also for crystalline materials or for nanocrystalline materials, and here it is presented the faceted relief inside the indentation that demonstrate the rotation plasticity on the example of gallium fluoride and gallium phosphide and calcium fluoride crystals. And here you can see the twins on bismuth stibbium crystals, and the rotation plasticity, the main mechanism for the deformation of nanocrystalline material. This is intergranular slipping. The second factor influencing the relaxation processes is strain, and different strain can be created by different indentures depending on its geometry. And we find out that for example, Berkovich and Vickers indentures can create different strain rate, and the mechanism of deformation change for the same load, the same condition, only because of the using of different indentures. We can see here facility to relief inside the Berkovich indentation, and know these signs in the Vickers indentation. As well, the well-developed fracture around Berkovich indentation and a pure plastic deformation for Vickers for the same load applied. We calculated the strain created by Berkovich and Vickers indenture and find out that for Berkovich create much higher strain of 10.3% comparatively with Vickers one, 7.9. And as well, we use for the calculation the modified Zhidonis and Vasauskas formula by taking into account the tip rounding, because any indenture could not be fabricated ideal sharp and has always rounding at the tip, and the tip, this rounding is smaller for Berkovich because it's trihedral shape and can be more fabricated more sharper. And and here the calculations show that for the initial stages of penetration, this difference between Berkovich and Vickers indenture is even higher than this one demonstrated here. So this is the reason of these differences in mechanism of deformation. As well, the strain created on the indenture may be induced by load value. And here you can see on the example of cadmium gallium sulfide crystal that the increase of load induce the plastic fragile transition. The load applied from 20 to 100 millinewton, and you can see this big difference in the mechanism of deformation. And as well for borophosphate glass, also the indenture made at 50 millinewtons demonstrate no cracks around the indentation, and for high load applied, you can see well-developed cracks around the indentation. The next factors can be unified as time-dependent factors, and namely loading, strain rate, prolonged loading under the peak load, and cyclic loading. And I will stop on these two. So on the example of silicon single crystals, we investigate the influence of different holding time, long holding time and short holding time. And here you can see the deformation curve and the well-known event, pop-out event, which is responsible for the transition from beta sternum silicon 2 structure to base-centered cubic structure. And with longer holding time, this pop-out event changed to kink pop-out event. And the Raman investigation showed that for longer holding time, the amorphous phase is formed, and namely in the depths of the indentation. And for short holding time, this amorphous phase is formed just at the surface. And we assume that during long holding, the amorphous silicon is formed in the depths of the indentation as a result of the activity of the dislocation. And this results is confirmed by the TEM investigations, which show that these amorphous phase are created in the shape of the bands along the 111 direction, the direction of preferential main slipping plane of a silicon. And in such a way, we demonstrate that the holding prolonged holding under the load is also a factor that influences the change in the relaxation processes and mechanism of deformation. The next time-dependent factors is loading rate, or why we use this bracket loading strain, because we use when perform the measurements, we use the loading rate, but in mechanics the strain rate is more important notion. But we demonstrate that the loading and strain rate are proportional, directly proportional values, and we calculate that the strain rate is also higher for higher loading rate during the penetration. You can see here the stage of loading, and for the first initial stages of deformation, the strain rate is even much more higher for higher loading rate. And this is correct for low loads and high loads as well. So on the example of aluminophosphate glasses, we demonstrate that the mutual due to the change in loading rate, the mutual contribution of densification and plastic flow changes as well. And the densification during indentation can be estimated by annealing the indented samples, and the volume recovered after annealing show the degree of densification. We investigate three low values of loads: 20, 100, and 500 millinewtons. And for all these loads, the higher loading rate decrease the densification during indentation. This is again a result that confirms that loading strain rate can induce changes in mechanism of deformation and relaxation processes. One more interesting results, which was obtained during lateral mode of point contact deformation, namely scratching of silicon law 1, influence of strain rate or scratching speed, and again strain and strain rate and scratching speed are directly proportional, and you can see here the calculation of strain rate depending on the scratching speed, and for high scratching speed the strain rate is several order of magnitude higher than for low scratching speed. And the increase of scratching speed induces transition from brittle fracture to plastic extrusion and ductile cutting. And this is an inverse results comparing with the static indentation, because with increase of load during the indentation, as I showed, induce fracture. And here the fracture is happen because the indenter what is scratching, the indenter is loaded and then moved with the lateral force, and as a result the groove or scratch remain on the surface. And when we move with low speed, the materials, the brittle materials like silicon fracture, and with the increase of speed due to the transition from silicon 1 to silicon 2, metallic, more plastic phase, the plastic deformation can be developed, and then by increasing further the speed of scratching, the mechanism change into ductile cutting, and this is the result of a specific displacement of material during scratching. The material is displayed ahead and then by side, and with the increase of scratching speed, the material, the velocity of this plastic deformation is not sufficient, and the internal stresses increases, and at the critical stress the material is energetically more effective to deform by ductile cutting. In this case, the material is removed and not extruded, and not accumulated ahead. And here you can see a mapping of the mechanism of deformation for both edge-on and face-on moving of the indenter. And you can see that it influences as well the values of hardness. And during the plastic extrusion, the hardness increases with the increase of load. And then when the critical stresses are reached, the hardness decrease and then set constant, and at the maximum scratching speed of 300 millinewton per second, we can see no difference between different normal loads applied. And finally, the temperature is the one more factor that influence the mechanism of deformation under micron-Dunn indentation. And here one can see the indentation on lithium fluoride crystal, the room temperature, and the same load applied, and the temperature of deformation is 77 Kelvin. And one can see here the appearance of well-developed crack and the slip lines. With the increase of load, as I said before, the mechanism change from plastic to fragile. For room temperature, we have these aspects of indentation, and with the decrease of deformation temperature, one can see a fragmented structure that is the sign of rotation plasticity, and as well we obtain one more confirmation of this. This is splitting of spots in the levogram during XRD measurements. The obtained results led us to conclude that the relaxation of the internal stresses under indentation begins just during loading by dissipating the stored elastic energy into the irreversible plastic deformation. It continues during the holding under peak load, if any, entering the active relaxation phase during unloading till full load release, after which the final relaxation phase is set in. The whole relaxation process is influenced by several main factors: structure of material, strain created by indenter depending on its geometry and load applied, time-dependent group of factors that include strain rate and prolonged holding under maximum load, and temperature of deformation. Thank you very much for your attention.
Thank you, Dr. Olga. That was really awesome presentation. Thank you so much.
Thank you.
We're open to questions now. Any questions for Dr. Olga? Next speaker is Dr. Yinfu from Ningbo Institute of Materials Technology and Engineering, China, and he is going to give a presentation on CNT wheels interleaved CFRP composites with enhanced interlaminar fracture toughness. And I request Dr. Yinfu to start his presentation.
Okay. Thank you for the introduction, and also thank you for the invitation to give this presentation in front of you. Okay, let's get started. So the topic today is the CNT wheels interleaved CFRP composite with enhanced interlaminar fracture toughness. So firstly, I would like to give a brief introduction about the background. As we all know, the fiber reinforced polymer with high specific stiffness, strength, and excellent fatigue properties is widely used in various areas like the building reinforcement, the windmill, the racing car, bicycle, and aircraft, etc. This material normally consists of different plies with different directions. So the failure mechanism can be divided into two different categories: the intralaminar failure and the interlaminar failure. Compared with intralaminar failure, the interlaminar failure actually is more harmful, and it normally happened when the structure suffers from the loading cases like impact, compression, fatigue. And once it's happened, the integrity or the stiffness of the whole structure will suffer great. So it's extremely important to reinforce this interlaminar property. But how? The traditional toughening methods like 3D woven, the pinning, or stitching actually is quite helpful and effective. However, there are some drawbacks. the fiber damaging, stress concentration, and the loss of in-plane one refraction with these methods will finally result in the reduction of the in-plane properties. So some researchers propose, why don't we directly toughen the weak layer, the interlayer? For example, by spraying thinking solution on the surface of the track or the fabric. However, there exists a negative influence of the solution left over on the mechanical property of the laminate. Then people try to use random-oriented thinking fabric, the bulky paper, so to serve as an interleaf material to reinforce this weak layer. The drawback of this material is that the permeability is quite low, so actually it's very hard to make the resin fully infiltrate inside. And recently, also people try to use non-woven microfiber wheels. And compare with this bulky paper, the porosity is quite high, as you can see here. So the resin can be easily infiltrated inside, but the diameter of these wheels is in the range of micrometer. So actually, the thickness of these wheels is quite high. Just imagine when you interleave a lot of material inside the laminate, the whole thickness and the weight of the whole composite material will increase a lot. And very recently, the electron spun nanofiber wheels draw a lot of attention. Firstly, the nanoscale diameter enable us to make ultra thin interleaf material, and also this material has a very high porosity, so the resin can be easily infiltrated inside. Actually, this material has already commercialized in interlaminar toughening region. Actually, in our lab, we can produce a more competitive material. We call it thinking fiber wheels. And we can also tailor this material. For example, by changing the promoter concentration, we can change the thinking types. And by adjust the Joule rate, we can produce the thinking wheels with different configurations, like randomly aligned or aligned. And most importantly, we can also tailor the porosity of this material by using different densification methods. And also, compared with electric spun nanofiber wheels, these thinking fiber wheels has a lot of advantages. Firstly, the smaller diameter enables us to make the thinner interleaf materials. Second, the better mechanical property of the thintees enable us to build a more stronger mechanical link between the plies. And also, this material has exceptional electrical conductivity and a very high surface area. So it finally will give the laminate multi-functionalities like energy storage, damage sensing, etc. And based on this material, I developed a new method to make nanocomposites. And firstly, directly collect the thinking wheels on the surface of carbon fabric. The surface of this fabric should be wavy, so under welcome back pressure, these thick and fluffy thinking wheels will be pressed into thin thinking fiber films with waviness. Then I do the infusion to fix this structure. Here's some details. I use release film to serve as a plug. And I also use 2 layers of infusion media to promote the resin flow. Here's a video of these VATM methods. As you can see in the video, with the help of the infusion media, the flow speed on the surface actually is quite fast. But in order to guarantee the thinking wheel inside can be fully infiltrated by the resin, we purposely leave a 3 centimeter blank area here As you can see here, when the resin float reaches this region, the flow speed slows down greatly. In this case, it leaves more time to fulfill the resin infiltration along the through the thickness directions. With these optimized methods, we finally get the laminate with a very good quality. As you can see here, through the scan imaging and also the processing imaging from the optical microscope, we can find that it is no micro voids inside the laminate. And also here, the CNTs are well distributed within the interlaminar region. And then we perform DCB test, double cantilever beam test, to evaluate the model 1 fracture toughness. We totally prepare 4 different groups. The first group we call it as the produced CNT views. In this case, we continuously collecting CNT views for 30 minutes. The second group we call it partially densified CNT views. We collect 5 minutes and then we use acetone to densify these CNT views. And then we finish the other 25 minutes collection. The third group we call it commercial CNT views, which is fully densified. As you can see here, the surface actually is quite dense. And the baseline sample, we use nothing. And here, we can get the test result by doing the DCB test. And by using the modified beam theory, we can get the R curve, which is the delamination length versus the model 1 energy release rate. And we use this propagation value to serve as a fracture toughness. As you can see here, the sample with as produced CNT views, the model 1 fracture toughness enhanced as much as 60%. However, when you use densified CNT views, the model 1 fracture toughness degrades a lot. What happened? By examining the fracture surface, we can find the reason. The sample with the fracture surface or the sample with as produced CNT views, the fracture surface actually is quite rough and there exists melt-scale fiber bridging. As you can see here, there exists macro-scale carbon fiber bridging, and also here, there is CNT fiber bridging. However, the baseline sample, the fracture surface actually is quite smooth and flat, and there's no fiber bridging, which corresponding to this kind of flat R curve. And also the sample with commercial CNT views, the fracture, there exists a lot of sweet-like peeling, and actually there's you cannot find any fiber bridging inside. Then we would like to scale up these methods from lab scale to industry scale. We perform joint work with Tortec company. Previously, we use a commercial CNT wheel from Tortec to get one bad result. Then we try to optimize the methods. We directly send the carbon fabric to the company, and based on our suggestions, they do the in situ CNT view stabilization on the surface of this carbon fabric, and then they send this material to us. We finish the laminate manufacturing and also the later characterization work. The purpose of this joint work is try to develop and also industrialize proposed methods for CNT implementation in structural laminate composites. And also, since we can get enough material, I perform a systematic investigation about the thickness effects of the CNT interleaves on the interlaminar properties of these woven self-RP composites. Here shows the image of different CNT views The first one is the mass centrifuge. You can see the surface actually is quite dense. And the next one is we propose methods to make these centrifuges. As you can see here, actually the porosity is quite high. And here, then we use TM methods to make the laminate. Here we also propose a new method to get the model 2 sample. We directly made the model 2 sample from the model 1 sample. In this case, we can clearly see the transition region from the model 1 case to model 2 case. Here shows the cross-section image of these samples. We can find the sample with a centrifugal thickness of 7.5 GSM, 1.0 GSM, and 1.5 GSM, corresponding to a centrifugal thickness of 5, 10, and 15 micrometer, which is quite small. And here is the result. As we mentioned before, the sample with the mass centrifuges, the model 1 fracture toughness degrade a lot. Surprisingly, when we use the in situ mechanical densified centrifuges, the model 1 fracture toughness enhanced as much as 76%. However, when the area density increased up to 1.5 GSM, there exists a huge degradation, which should be ascribed to the pore resin infiltration. And interestingly, in model 2 case, with the increase of the area density from 0.5 to 1.5 GSM, the model 2 fracture toughness continuously increased. So it seems there exists different toughening mechanism in model 1 and model 2 case. For example, in this 1.5 GSM centrifuges, it can greatly degrade the fracture toughness, model 1 fracture toughness, but it can greatly improve the model 2 fracture toughness. What happened? By examining the fracture surface, we can find the reason. We find actually from model 1 to model 2, there exists crack diffraction. In model 1 case, the crack actually only propagates inside the centrifuges, but in model 2 case, there exists a lot of this kind of interlaminar crossing inside the laminate. This is the main toughening mechanism. Okay, let's get a conclusion. Firstly, the centrifuge is a promising candidate for interleaving application. The toughening effects of the centrifuge depends highly on the thickness, the degree of compression, as well as the loader condition, like model 1 or model 2, etc. The second, densification of centrifuges will solvent exposure will lower the permeability and thus inhibit through the thickness percolation of the resin in the infusion methods. Third, mechanically densified centrifuges onto the surface of carbon fabrics proved to be an effective way to improve the interlaminar property of woven self-RP laminate. Finally, the interlaminar crossing play a paramount role in toughening mechanism. The crack front alternatively propagate above and below the single toughness region, significantly improving the fracture toughness of the resultant laminate. Okay, thank you for your attention. Question, please.
Yes, thank you, Dr. Infu, for your nice presentation.
Thank you. Is there any questions?
Our next speaker is Samuel Bertolini from University of Germany, and I request Samuel to start his presentation.
Thank you. I'm going to
try to share the presentation if I find the button, share screen. I hope that you can see my presentation.
Yes, we can see.
Great. I'm from the University of Ulm in south of Germany. Our research group, the research on electrochemistry. And what I'm presenting here is a method that we use, a computation method called DFT, density function theory, that calculates the energy and distribution of electrons by plane wave. With this, you can obtain electric properties, mechanical properties, chemical properties. The investigation that I'm going to present here, the focus is in lithium sulfur battery. In the case, more precise, in the cathode, host material cathode for lithium sulfur batteries, that in the case is a conductor polymer called sulfur polyacrylonitrile. Why to do this kind of investigation? Today, the majority of the electronic application that exist use lithium-ion batteries. There is many applications here. For example, you have even the contradiction between medical equipments that they use batteries to save life, and this drone here that's a military application to destroy lives. Of course, there is luxury cars. This is Pagani. It's an Italian electrical car of luxury. There is more simple cars. There is main application. Right now, someone that's watching the presentation is in front of a laptop or is watching through a smartphone that also has lithium-ion battery. And of course, the generation of electricity by solar panels or by wind power. They have oscillation from the natural source. And during this period that the source is extremely low, it's important to have a battery to absorb this excess of energy and use in a later period of time. In other words, when you need to accumulate electric energy to use, you convert in chemical energy and then you convert back when it's necessary. Why lithium sulfur batteries? Is because the potential to increase the specific capacity is more than 4 times. So what means if you have a car right now, they can run 500 kilometers. With the lithium sulfur battery, it can do 4 times more, 2000. Because of how is inside of the battery? So the battery is separated in an anode, that's the negative electrode, in a cathode, that's the positive electrode, and between them there is a separator to not allow them to touch and conduct electricity, and also to conduct only the ions. Inside of the anode, in the case of lithium sulfur battery, you have a lithium metal, and the lithium metal is very reactive. It reacts with the electrolyte, and inorganic and organic salts is deposited, as you can see here in the figure. This is called the solid electrolyte interface. That's an important characteristic of anode. In the cathode, you have the active material, that's sulfur, and the problem is sulfur does not conduct electricity. So it's necessary host material. Normally the batteries is a carbon, that's the host material. And the biggest problem of the sulfur batteries is the formation of soluble salts contain sulfur rings and lithium, and they move, they shuttle from the cathode to the anode, they decompose in the surface, consuming the battery, and they can also shuttle back, bring lithiums to create a self-discharge. In other words, although the specific capacity of these batteries is high right now, the life is relatively low. Go inside of the anode and show a little bit here how the solid electrolyte is formed. Here is a solvent. The solvent in a no-aqueous solution, they transport the lithium ions by absorb lithium ions on the oxygen sides. In the surface of the lithium metal, they can decompose, they form ions, and those ions form lithium oxide, lithium carbonate, and later, after longer decomposition, it forms organic salt, kind of polymers. As you can see here in this side, this is another big problem of the anode. This sort of electrolyte interface breaks. It creates a preferential path for the lithium to deposit during the recharge of the battery, and it forms the dendrites. The dendrite grows, has an extremely high volume. It touches the cathode and conduces a high amount of electricity in these very small, very thin structures, heating up the organic solution and exploding the battery. Inside of the cathode, as I said before, there is the formation of polysulfides. That's those sulfur chains with lithium attached. How people use carbon, one of the biggest strategy to reduce this short of the polysulfide is trying to confine inside of the cathode. One method that they use is change the architecture or the morphology of the graphite. You can use carbon nanofibers. You can use this kind of structure that's produced from polymer, then heat treatment. And another way to reduce this shortage is to absorb the polysulfide inside of the battery by electrocatalyst material. So for example, the titanium oxide. So that they can absorb the polysulfide and they can accelerate the conversion of the polysulfide into lithium sulfide and spread this on the carbon. This is an example of the synthesis, and to show the importance of to have a high amount of this kind of active materials to improve the battery. They have here the example of the difference between the specific capacity in the two batteries and how this short of the polysulfide can completely change. What I'm going to present here is a completely different kind of host material. So in other words, I'm trying to replace the graphite. And why I'm trying to replace the graphite? The graphite is van der Waals interactions between the sulfur. This means weak interaction. It can form some chemical interactions in when the interlayer is exfoliated. So the polysulfide can chemically bound to the defects of the graphite. But here the strategy is a little bit different. As you can see in this image, you have a very high specific capacity for a long number of cycles, 1000. Of course, this needs to be improved. But as you can see, the sulfur can chemically bind to the polymer and then form the lithium sulfide around the polymer. So how is the synthesis and what's the importance of this? First, it starts with polyacrylonitrile synthesized together with sulfur, and the sulfur removes hydrogen from this polymer, which allows the formation of a carbon-nitrogen bond. It forms a sigma structure that can conduct electricity. So the sigma bonds can move, so conducting the electrons through the structure of the polymer. Later on, those cyclic structure is formed, hydrogen on top of carbon can be removed, and then if there is sulfur available, it attached to the sulfur chains during the synthesis, which means that I can also have undecoordinated carbon during the synthesis. What I'm doing, the research now going and concentrating inside of my research, this undecoordinated carbon that I just say, it can be formed during the synthesis. It's represented by undecoordinated carbon here that I'm showing with the iron. Also in this structure here, in this case, I consider the polysulfide a red binded. It can also be formed during the discharge. So suppose in the figure B here, I have the polysulfide attached, that sulfur is yellow, nitrogen blue, carbon gray, oxygen is red, and lithium is purple. So if there is a lithiation enough, it can remove this carbon sulfur bond. So there is a change during and they are also reconstructed. What I want to investigate here is, first, if this undecoordinated carbon can capture the polysulfide, which is a very important phenomenon that you would like to happen. Then the interaction of this undecoordinated carbon with the electrolyte, with the salt, and also with the solvent. And the effect of the salt, that's TFSI, when in presence of the polysulfide, and how it can affect. So going to the next, the capture of the polysulfide. This is the image running from to a total of 15 picoseconds. In the beginning, I have the polysulfide solvated in the electrolyte. It has a distance relative of 5 Armstrong. So in the next step, you can see that the first thing that happens is the polysulfide is attracted by the undecoordinated carbon. This process makes the sulfur chain to break, and one of the sulfur get attached to the polymer. This means that the undecoordinated carbon, the polymer, can capture the polysulfides from the electrolyte. Although the problem is they still form small chains of polysulfide. Then in the next step, the lithium that was before kind of solvated, it get attracted by the polymer, by the nitrogen sites, while the polysulfide is electrostatic interacting with the sulfur chain. In the next step, as you can see, the sulfur chains goes further, and the lithium completely is absorbed by the polymer. Why this is important? Because what you are calling the host material that should not interact is actually acting as an active material, a sulfur, which is positive. In a certain way, you want to absorb lithium ions to make the battery to run. Then what you can see in the next step, which is very interesting, is the polysulfide is reconstructed here, and the sulfur chain is rebuilt. And then the last step is a reconfiguration. The lithium goes in the direction up of the polymer backbone. You have an increase in the distance between the attached sulfur and the edge of the sulfur chain, and the lithium stay on the edge. Going to the next point, what I'm trying to show here is two things. The charge distribution between the solvent and the reaction that happens between the solvent. The solvent is represented by this molecule, and here the polymer backbone, and in this point is located the undecoordinated carbon. The first thing that happened is the attraction of the oxygen to the polymer, it bounds, and then the solvent breaks, create a new ramification. You don't know exactly if this is a positive thing or not, because in one way, it reduces the number of sites to capture the polysulfide, but at the same time, it creates new sites for the absorption of lithium. And beyond this, the carbon here are still under-coordinated, which means that it can create maybe a cathode electrolyte interface and may protect against the shot of the polysulfide. But the capture of the polysulfide with time during charge and discharge of the battery tends to reduce. Of course, this is going to depend of the configuration of the polymer, because if charge and discharge, these under-coordinated carbon can be more stable or not. The polymer here, they don't transfer charge to the backbone. So in the beginning here, the charge distribution here is neutral, and then after that attach and it decompose, it continues neutral here. So there is no transfer of charge, but there is a redistribution of the charge. As you can see, oxygen and nitrogen accumulate electrons. Carbon, so it also in one side of the polymer, you have a negative charge to absorb lithium ions, and the other side is relatively neutral. And there is just an exchange between this carbon that later becomes a little bit more neutral with a relatively positive charge. In the case here, red means positive and blue means negative. Then going to the effect of the salt. As you can see in the beginning, is relatively the same that I showed before. So the polysulfide get attract. The mechanism of where it breaks is not really important in the case, although it tends to break in the middle of the sulfur chain and form a structure that's attached to the cis and another that's unattached. The mechanism here is different, but it's not the important thing here. The most important thing in this part is the last two figures. When you have the salt solvated, the main difference before you have the same time, 15 picoseconds, and still the polysulfide is not completely reconstructed. And beyond this, the salt is enough to remove the lithium from the polysulfide attached and reducing this reconstruction. In another way, in many cases, the salts is used in high concentrations to target the formation of dendrite that I said before. But here it plays a negative role. It reduces the time for the sulfur chains to be reconstructed. And then the question if the salt can react with the under-coordinated carbon is actually it doesn't, apparently it doesn't. Just to say what's the structure here, the cyan is fluoride, carbon, sulfur, red is oxygen, nitrogen still blue, and sulfur yellow. I'm just marked here the under-coordinated carbon to show the location, but this is carbon and hydrogen is in white. So there is no reaction here. But at the same time, there is no reaction with the solvent. Going to this point, it's we know that the under-coordinated carbon can capture the polysulfide. So the idea was to try to understand the possibility for some specific salts to remove hydrogen from the polymer, and if this new under-coordinated carbon can be created and react with sulfur. What I'm showing here is the bound stray between carbon and hydrogen. So closer of zero, weaker is the interaction. more negative, stronger is in their interaction. I have here CH1, which means the position of this hydrogen here, and successively all the hydrogens here, as you can see the polymer in the background. This line here is to show the average carbon hydrogen in the solvent, because if I use a protophilic salt, there is a possibility to react with the polymer or with the solvent. But the important point here is, after this absorption of the polysulfide, the hydrogen carbon interaction becomes weaker. And there is, of course, that there is carbon hydrogen solvent that can be weaker than the polymer, but it shows, since thermodynamics is also an average calculations in general, there is probably a competition between the solvent and the polymer to react with those salts. But this, in this part, this is the first assumption, and there is still no kind of experimentals with this host material. But this is something that would be very interesting to do. To finalize, what I'm going to show you here is the projects going on. I just presented the first part here. There's the capturing process over the undercoordinated carbon. There is other projects that is also been meted or finishing for publication. This part here, the B, what I want to see if the sulfur can create a cross section and how initial lithiation can affect. Actually, the lithiation affect and doesn't form the cross section, and without the presence of lithium, it forms the cross section between the two different polymer backbones. So the cathodic reaction, actually it happened. So the salt, what I observed, and of course is depend of the structure of the polymer and the amount of lithium absorbed and so on. But the salt that was a photophilic reacted with the solvent, not with the polymer. In this case, it's the capturing of the polysulfide when I have a certain amount of sulfur in the undercoordinated carbon, which is a little bit different than before. And actually, it can also capture the polysulfide up to a certain limit of the size chain, and then start to form sulfur, because the polymer capture more lithium ions than the sulfur attached. Then the lithiation process to simulate this charge, and there is a distribution of charge between the polysulfide that breaks the chains at the same time that's captured by the polymer. And finally, the capture in multiple sites. So I have another undercoordinated carbon here. It cannot form an enclosed system under a small lithiation. It not necessarily react with the solvent, but it can also react depending of the structure. But you observed here that not always that the solvent react. I hope that I did in a good time. I'm going to open for questions. If anyone has any question, please let me know.
Okay. Our next speaker is Antonio Magna Hernandez from Arbomax, Mexico. And I request Antonio to start his presentation.
Well, okay. Good evening. Well, good morning here in Mexico. I think good evening, good afternoon for you. I'm not sure. Well, thanks for the time. Thanks for the attention in advance. I am Antonio Magalla. I'm from Mexico. I am a metallurgical engineer, and I work at Arbomex in the R&D department. Today we are talking about microstructural and mechanical assessment of camshaft produced by ductile cast iron. The topic is the ductile cast iron low alloyed with vanadium. So before to start, I have to say some this slide is about Arromex company profile. About this 2021, so number of employees, I have to say that Arromex is a completely Mexican company. We have three molding process for cast iron. We have a cold box process by stacking mold, no bake molding or no bake process, and loose foam. And we have high pressure die casting for aluminum. Some of our clients, you can see Stellantis, Kawasaki, Daimler Trucks, Ford, Packard, Mazda, Emerson, American Axle, Murakami. About our products, the main product, the specialty is camshaft, but we produce crankshaft too, brackets, housings, water pump, balance shaft, and our presence, we are in Guanajuato. We have 2 plants. In the first plant in Celaya, we have the iron foundry and the iron and steel machining. In the second plant in Apaseo, Guanajuato, we have the iron heat treatment by induction hardened and machining. And in this plant, we have aluminum high pressure die casting and machining too. Yeah. So to start, I would like to show you this chart for ASBIS, where we can see the development of materials over time. Iron was discovered in the 1500s. Yeah, but ductile iron born until 1940s. And today it continues to be an alternative for use in high performance applications. So the ductile iron continue being important material for application in engineering. In the next slide, we'll continue with ASBIS on materials engineering or selection of these materials for engineering applications. ASBIS divides the materials in 4 groups: glasses, polymers, ceramics. The interest group for us in metal is metals, when we find aluminum, steel alloys, zinc alloys such as SAMAC, and cast irons. The question about this is, what is the future of these materials? We have 6 points. According to market trends, we have 6 important groups. The ferrous materials with steel alloys, special steel alloys, and cast irons, advancing cast irons. Functional materials and materials for e-mobility, lightweight metals such as aluminum, fiber reinforced materials, in this part into the composites, production processes and industry 4.0, and plastics, automotive and aircraft applications. So in Arromex, we are working with 3 of them: ferrous materials, lightweight metals, and production processes and industry 4.0. About a future roadmap of materials in Arromex, we have these 4 points. The first is additive manufacturing. We are working with some metals, titanium alloys, some polymers. And in cast iron, we have the SSFDI. This is a new generation of ductile iron. The specification is from Europe. about 2016, more or less. And austemper ductile iron is a common material today, nowadays. Prototypes in process. We are working in SAMAC. We project the next year. We are working with SAMAC production. We are working with graphene too, and aluminum high pressure die casting for automotive applications. Here are some of the developments and applications. For the additive manufacturing, we have 2 points. We are working with prosthetics. Arromex has a community service in Mexico. An internal tool application or develop of prototypes, quickly prototypes. In cast iron, we have 3 new alloys. Is our offer to the clients. And the first is W315 alloy. This is for highly wear resistant. In the matrix, we have some carbide. Heavy alloy is a material today is in process patent. And TS206 alloy is the material to replace, to assemble steel camshaft. And we are been working on graphene films in material. In linking work with CIMAP Mexico. Well, about the topic of today, the initial studies and trials for the development of TS206 alloy. This is the name, the commercial name. The new commercial name. The purpose of this presentation, this work is divided into 2 parts, ASCAS and heat treatment. And today we are working about ASCAS condition. About the metrics, the nodule counts, the nodule size, the quality of these nodules. And what is the objective? What is the purpose of this job? Well, the substitution of assembled steel camshaft by ductile iron, non-tempered ductile iron camshaft with similar mechanical characteristics, and the most important, with wear reduction. This is for the powertrain, and it's an important topic in the automotive industry. And why continue working on components to internal combustion engine? Well, the camshaft use remains a key part on new vehicle platforms. If you can see the projection around 2030 in global market tell us that the camshaft will continue to be used in the about 90% of them or more in 90% of them. And if you can see these platforms, they are hybrid cars. The internal combustion engine, the middle engine vehicles, hybrid electric vehicles, plug-in electric hybrid vehicles, all of them use a camshaft. So about this information, we are working to develop this part. The work has a title, Microstructural and Mechanical Assessment of Camshaft produced by Dr. Casaro, Lower Big Vanadium. This is the team. Three people from the Metallurgy and Materials Department of Instituto Politécnico Nacional, and Jaime Telles and I from Arromex department, the R&D department. So to start, what is a camshaft? What is a camshaft? Well, this is a part in the powertrain, in the engine. So it's a part in the. I'm sorry. This is a video. Okay, it's a part in the powertrain who performs by a mechanical movement, the opening and the closing of the combustion chamber in an engine. And the engine downsizing is a well-known way of improving fuel efficiency in an internal combustion engine through reducing weight, while turbocharging is used to maintain peak power from the engine because of these mechanical requirements or the mechanical properties in the material, or in this case, the components are becoming more demanding. Here we have some paper highlights, the three most important, I think this. Well, the first, the as-cast ductile iron, this as-cast, this project, this material, was considered a raw material for the heat treatment of tempered ductile iron camshaft production. As-cast condition is the first part of the development. The second part is the heat treatment, is the tempering. The second, say, the process to obtain the mold was Novec, one of the most common molds, very, very common, such as green sand, that allows three-dimensionally repeatability and high production rates. And the number three, vanadium, was tested at, at levels of 0.2 and 0.3% in a pyrolytic matrix. So about ductile iron production, we have four main steps. The first is where we add the vanadium. Yeah, we have to control the chemical composition in the melting furnace. The chemical composition is copper, manganese, silicon, carbon, magnesium, etc. But in this case, it's all of them, of these elements, more vanadium in 0.2 and 0.3%. The second is denobilization. With the magnesium in the ladle, we form the nodules. We can round particles or graphite particles. And then in the inoculation, I'm sorry, we add ferrosilicon and we can increase the nodular count. Yeah, this is important for a good quality in ductile iron. And then at the end of the line, we can pour in the metal into the molds to obtain the part, or in this case, the camshaft. In this slide, we have the image about the prototype cluster with 4 camshafts, 16 lobes for everyone in V8 engine. We have the camshaft, the fading system, the riser, and we mark 4 lobes, 1, 6, 11, and 16. On the right, you can see the lobes with analyzed zone along the camshaft, in the top, in the middle of the camshaft, and in the bottom of the camshaft. The most important zone is the top, because this is the sun, the hardened sun. This is an example, yeah, about the material characterization of the paper charge in the paper, in the article, and the nodule size is different along the camshaft, and even in the same lobe analyzed. This is caused by the solidification rate and part thicknesses. If you can see in the lobe 1, 6, 11, and 16, we have different results for the nodular size. Yeah, different results for the top zone, for the middle zone, and the bottom zone in 0.2% and 0.3%. The result summary tells us that with the vanadium addition, we have a nodular count increase, and that we have smaller nodules. The addition of vanadium increased hardness and carbide percentage. And the important here in this slide is the hardness. If you can see, without vanadium, we have more or less 2A7 hardness in beakers. But when we can add vanadium, this hardness increase. So the literature reports that the addition of vanadium to the ductile iron decrease the nodule count and nodularity of graphite. But in this work, in this part, in this project, we have a higher nodule count and nodularity with addition of vanadium. This can be for the inoculation method, but today we are talking about the vanadium percentage or the effect of this percentage of vanadium. About the mechanical properties, well, we have an increase about yield and tensile strength in 0.3% in comparison with 0.2% allow. The elongation is affected by the carbides present in both materials. And for mechanical testing, we obtain samples of the camshaft and the keel blocks according to the international standards. And the results are the average of these parts. To conclude, in short, we have 2 points. The graphite quality of the camshaft depends on their section size and in the position of the fading and guiding system. Along the camshaft in every lobe number 1, lobe number 16, in the same lobe, in the top, in the middle, in the bottom. The amounts of copper and manganese and vanadium in this case add to the cast to improve the temperability in subsequent heat treat process. The yield and ultimate tensile strength in camshaft were increased by adding 0.3% of vanadium. However, the toughness and ductility, as you can see in the chart, decreased due to the presence of carbides. The carbides, the final carbides is around 1.2, 1.3 in the max in this alloy. So the main conclusion is the ductile cast iron with 0.3 vanadium is adequate alloy for temperature process for the heat treatment, the next heat treatment. Thank you so much. If you want to know the paper detail or more about this paper, you can visit the page. This is my contact, my email address, and the article is completely open access. If you want to read, go ahead. Thank you so much. Thanks so much for the time.
Thank you, Antonio, for your excellent presentation. Our next presenter is Mr. Nargopal Manna from National Chemical Laboratory, India. And I request Nargopal Manna to start his presentation.
Sure. So good evening to all, and thank you the Global Scientific Guild for giving me the opportunity to present my work. So that the title of my presentation is the zinc air batteries catalyzed using cobalt oxide nanorod supported nitrogen doped entangled graphene for oxygen reduction reaction. So here in this work, what I done that for zinc air battery I have done and preparing. I have prepared the cobalt oxide nanorod supported the nitrogen doped entangled graphene, which is a one kind of 3D graphene, and have checked the half cell level RD study. So before going to my work, I'll go through some introduction. So next. So as you know that the globals is the global wise there are several issues we are facing. So the based on the Rice University study suggested that the humans top 10 problems for the next 50 years is like various kinds of problem like energy, water, food, environment, poverty, and other things. Although which all are correlating to each other. So but there are few main important things those are now like the research are going on like energy and environment. So how energy has direct impact on the environment. If you see in the transportation and portable and stationary section, where the energies are mostly using for various sector, so which are coming from the major energy sources like coal, hydroelectricity, renewable energy, and natural gas. Although the renewable energy sources is very less percentage, only 12% sources are using for energy, but mostly it is coming if you see the coal or which is showing giving the 59% energy are coming from the coal, which is carbon based fuel. So what happened when carbon based fuels are using for global wise the various effect like the carbon dioxide emission, 81% carbon dioxides are coming from the coal fuel, and other is like methane and nitrous oxide and fluorinated gas. If such way is continuing, so what will happen finally? Air, water, as well as the soil will affected by this kinds of carbon based fuel utilization. Next. So look into this issue. There are several ways people are trying to addressing this issue, like various renewable energy sources. Although the renewable energy like solar and the hydroelectric and the other sources are also focusing, but they are because of their intermittency nature, we need a particular solution to which can give the 24 hours electricity. And that can use the various energy purpose. So among them, the electrochemical energy devices are a good solution where you can utilize it for 24 hours. So here you can see the various electrochemical energy devices which has two different energy. One is the power density and one is the energy density. So based on their power density and energy density, which could be, if you see the supercapacitor, which has the very high power density, and so like the T20 as where the you have to make a good score in every movement, every ball, and every. But if you see the fuel cell and battery, which has the high energy density, so energy density is as long as you are supplying the fuel, so it will keep continue to energy. So like a test match, you have to stand there and you have to play for a long time. So for that you need energy only. So that energy and patience you can give the more time you can play. So if you see the fuel cell and supercapacitor, in between one thing is that the batteries. Although there are global wise lithium ion batteries are working mostly, but still there is an issue mostly with the lithium ion battery and sodium ions battery which are using, but lithium ion battery already has a state of the art device technology. But still issue with the lithium is that the lithium is not available worldwide because of the availability as well as the safety issue. Recently metal air batteries are also focusing to working as a very energy storage devices. So if you look into the metal air batteries, there are several batteries like non-aqueous and aqueous metal air battery. If you see the non-aqueous metal air batteries like lithium, sodium, and potassium, which are working in non-aqueous systems. So non-aqueous systems, although their theoretical energy density is very high, but still in practical solution there is a not that one technical or issue is there, and as well as the lithium and sodium can capture fire in air condition. So then you come to the aqueous systems like aluminium, magnesium, and zinc and iron air battery. So aluminium and magnesium and battery is not a suitable choice for aqueous solution because there is a passivation layer formation and other issue which practically the energy density is very less. Although the zinc air battery theoretical energy density is comparatively lower to aluminium and magnesium air battery, but still the practical there is already state of the art device setup is there, and people are working also zinc air battery. Although other benefit from the zinc air batteries like inexpensive nature of the zinc anode and the reliable and environmental friendly and less corrosive, as well as high theoretical energy theoretical capacity. Next. So if you look into the zinc air battery, how it is work actually. So in zinc air battery, there are one is cathode and another one is anode. So but in cathode reaction is the there are during the charging and recharge process, if you look into the only discharge process, so where oxygen reacting with the or oxygen reacting through 4 electron process and formation of the hydroxyl ion in cathode, and but that hydroxyl ion move towards the anode through separator or membrane and formation of the zinc hydroxyl ion, and then again it react with the two electron process and formation of the zinc oxide. So the overall reaction is the in zinc air battery in the during the discharge process is oxygen reacting with zinc, and through 4 electron process is transferred from zinc oxide and hydroxyl ion. So if the completely charging process, the completely opposite reaction will happen. So if we look into the this process here, the three things is there mostly. If the overall reaction, the oxygen gas, one is the electron process, and other things is the anode. So the complete process, which is oxygen reacting with the 4 electron process and formation of the hydroxyl ion, as it is the 4 electron process, kinetics is very slow. So further here in device setup, you can see there are three things. One is the solid, one is the gas, and other is the liquid. Three things are interacting together and forming the hydroxyl ion. Although these three things, when it is effectively combining, that time it's giving the better efficiency for a particular device. Although the solid gas and the liquid is fixed, that is electrolyte and the gas molecule is fixed for a particular devices. So next thing can focus on the solid catalyst. Although that catalyst is giving the better combination of the formation of the triple phase liquid, gas, and solid, and give the better overall efficiency of the devices will change. So now look into the other metal which are giving the better activity for oxygen reduction reaction. So from the volcano plot here, you can see the activity versus the energy plot. The platinum shows the best activity for oxygen reduction reaction compared to the other metal present in the period table. But still challenging issue with the platinum that highly cost, which is US dollar around $32 as per the 2019 report. And as well as second thing is the durability. For long-term performance, platinum has tremendous durability issue, which can combine with the CO2, or which can other effect like methanol that can react with. So that how to overcome these things. So people are now focusing on the other metal-based systems like transition metal oxides or spinel oxide or peroxide. Among them, the spinel oxides are getting into attraction. Can you go to next one? Yeah, so now people are focusing on the low cost transition metal hydroxide and oxides. Like spinel structure of oxides are getting very much attention for the electrochemical oxygen reduction reaction, because the spinel structure, there is a two metal atoms are presence in the two form. One is the tetrahedral and other is the octahedral form. So but both the presence of the two different crystal in tetrahedral and octahedral, and there are two different oxidation state giving the great advantage for redox activity for these spinel kinds of oxide. But still there is a limitation for the metal oxides, is that as the spinel oxides are semiconducting nature, so there is a conductivity issue is there. So that could be addressed by using the various advanced carbon support, which are last few decades the works going on the various carbon support development. So although there are carbon various 0 to 1 and 3-dimensional carbon already developed, but still the 2-dimensional graphene has a very unique properties because of their because of the 2-dimensional graphene can support various kinds of metal supports as well as, so that could be combined to the spinel oxide and the 2D graphene and give the better composite material for as a electrocatalyst. But further also the dopant and 2D graphene can increase the defects and S and dopant effect. Further tuning electronic property could be tuned. So although there are various reports are there, the nitrogen, sulfur, and selenium and all these things are doped over the graphene could improve the electrochemical performance and change the electronic property of the graphene systems. But the nitrogen could doped in various form like pyrrole, pyridinic, or the quaternary form of nitrogen could doped over the graphene substrate. So still there are issues that through 2D graphene is that as synthesis, the method already available in the graphene oxide synthesis. So they are forming more than one layer, like 2, 5 or 10 layers of graphene oxides, graphene are forming. So that during the electrochemical performance, there is a issue with that stacking issue, because after a certain cycle that can stack to each other, so that you suddenly drop the electrochemical performance. So what is my strategy in this work? So next slide. So what methodology I am using in this work, that the one is the oxide and other is the 3D graphene substrate. So oxide act as a catalyst, so that could be the performance could control by changing the morphology, or by various alloy or core shell. Or one thing I can do that is called intrinsic activity increases, that by tuning the morphology on shape and size. And one is the using what the support that also control the morphology and the support morphology also. So here I'm incorporating the 3D graphene, that is which has the high surface area and high electrical conductivity and high thermal conductivity. Also, main important thing is that the 3D graphene supported oxides give the better triple phase formation, which are already previously I told. The triple phase formation is the main important factor to get the better efficiency for a particular devices. So here I am preparing the one-dimensional nano rod of cobalt oxides over the 3D graphene. So because of the one-dimensional nature of the cobalt oxides, which giving a better electron transport mechanism, and because of the 3D graphene, there is a unique porous structure of the 3D graphene, give the better mass transport channel. So next. So this is my synthesis scheme. So here I am using as a graphene oxide as a precursor. So here I am using the cobalt oxide and ammonium hydroxide as a nitrogen source as well as reducing agent. So at particular pH of around 10, I am using the hydrothermal treatment, that is in presence of ammonium hydroxide, solvothermal treatment, and 180° 12 hours. So what will happen during this high temperature treatment? So metal particle will nucleate over the graphene substrate, and formation of at controlling the pH, I am tuning the morphology of the cobalt oxide. So, and finally, without any filtration, I did the freeze dyeing. I applied the freeze dyeing method to get the 3D morphology of the graphene. So here I have done the freeze dyeing at low temperature, around -50° centigrade. So finally, I got the material cobalt oxide nanorod supported over the nitrogen doped entangled graphene. That is entangled because of the graphene oxides are connected to each other to a particular angle through the sharing their edge. So further, I have demonstrated the Zinc-Air battery to check the better performance for the my catalyst. Next. So here you can see that, as I already told, that I prepared the 3D graphene that has high surface area and the better uniform porosity. So here you can see in the figure A, that is the graphene oxide. Initially the graphene oxide, then second one is the nitrogen of entangled graphene, which I prepared after the freeze dyeing without adding metal center. So if you see the two different observation for the graphene oxide and the nitrogen entangled graphene. So initial cases graphene oxide there is a stack structure, but after the freeze dyeing method applied, there is a uniform porosity are distributed. Similarly, when I am using the preparing the catalyst over the 3D graphene like cobalt oxide, so similar structure is forming the uniform porosity, and the nanorod over the 3D graphene are distributed. So I have to know the this is the first one is the FESM image. So here I am applying the tomography image also have taken to know the 3D morphology in various angle. So here you can see the figure D shows that the graphene oxide has the stack structure. The figure E is the shows the 3D graphene without metal substrate. There is a 3D structure and porosity are huge porosity are distributed over the whole over the substrate. And the last one, that figure F, here you can see also the almost similar structure is formed in presence of the catalyst, and there are porosity are there, which will help to better mass transport channel for the during the electrochemical performance. Next. So after checking the substrate morphology, here is the catalyst morphology, that is metal oxide morphology, to know that we have done that TM, HRTM, and analysis. So first figure A, here you can see how nanorods are distributed over the nitrogen entangled graphene. Figure B shows that how the nanorods are at higher magnified image, shows the nanorods are distributed over uniformly over the 3D graphene, that is nitrogen entangled graphene. And the selected area electron diffraction also shows the crystalline nature of the metal oxides form. Further, high resolution transmission electron microscopy, that is called HRTM. Here also you can see the nanorods clearly show the nanorod formation, and elemental mapping also suggested that the presence of all the elements like cobalt, oxygen, carbon, and nitrogen. And figure D and E, you can see the cobalt and oxygen over the nanorod are uniformly there. So formation of the cobalt oxide we can confirm from there. Next. So after confirming the morphology, so here we have done the XRD, Raman, BET, and XPS analysis. So from the XRD to the crystalline nature and what are the formation of the cobalt oxide over the 3D graphene, we confirm. Formation of the 301 peak is the most intense peak, which is responsible for the binding to the electrochemical oxygen during the electrochemical reactions. And further, the 3D graphene formation, as the graphene has a defective and graphitic peak, after incorporating into the metal oxides also what extent graphitization disrupt, that also checked. So here you can see the ID by IG value in figure B. So in 3D graphene 1.25, but after incorporating cobalt oxide into the 3D graphene also almost similar extent of graphitic figures there. So in presence of the cobalt oxide, there is no such change in graphitization, so which is a good indicator that 3D graphene, the graphitic structure is retained. Further, we have checked the BET analysis that the pore, as we are telling that the 3D graphene pore size is very much important. So here you can see in presence of the cobalt oxide also pore size are distributed in between 0 to 10 nanometer, which is because of the mesoporous nature of the graphene. Further, presence of the elements, and as the elements present as in electrochemical reaction, there is a very important thing is that what is the oxidation state, and so how it will affect overall performance. So here we check the presence of the cobalt and nitrogen and oxygen and carbon in figure D. And the presence of the nitrogen, as previous I told, that nitrogen get doped into the graphene in various form like pyrrolic, graphitic, and the so that also here we observe that presence of the pyridinic nitrogen carbon is very high. And further, the deconvoluted spectra of the cobalt 2P also shows that that here presence of the cobalt 3+ and cobalt 2+ ions. So next. So after confirming the formation of the cobalt oxide supported 3D graphene, so this is the things we have done the electrochemical experiment. So electrochemical experiment, firstly we have done the RD, that is ring disc electrode. So here ring disc electrode we have studied the cyclic voltammetry analysis, which is very useful analytical technique. So here we have done this experiment in 0.1 molar KOH in presence of oxygen and in presence of nitrogen. As why we are using the nitrogen, which is the very inert gas. So here to check the oxygen activity, first we are calibrating through nitrogen that whether it is showing any activity or not from the aqueous solution. So then we are purging the oxygen. So here you can see in the figure, sorry, here you can see the nitrogen entangled graphene. So there are oxygen saturation and nitrogen saturation CV. Here you can see there is a highly cathodic and anodic current gap is there. So because of the high porous nature, the conductive capacitive current are showing very high. But second one, if you see the cobalt oxide, that is in first one nitrogen entangled graphene without cobalt oxide, second one cobalt oxide without nitrogen graphene. So the because of the electrical semiconducting nature is showing very less current density for cobalt oxide. When we mix them, that cobalt oxide over the nitrogen entangled graphene, the sudden change in the limiting current as well as onset is completely changed and showing the good ORR activity. So also these catalysts, whatever we are preparing, although there are state-of-the-art catalysts like platinum carbon, which are showing by various company. So although we have compared their performance of ORR and their catalyst also, that state-of-the-art platinum carbon, so who is also showing the similar onset and the limiting current density. Can you go next? Further, we have done the RD experiment like linear sweep voltammetry, and from that we have calculated the TAFL plot. So first figure A, here you can see the in case of the cobalt oxide, the activity is very less, but in nitrogen of entangled graphene, so which activity is showing, although but there is still there is a E half and onset potential is high. Also further, when mixing together cobalt oxide over the nitrogen of entangled graphene, the activity onset potential is coming around 0.95, which is very close, means 50-volt millivolt difference compared to the state of the commercial carbon, platinum carbon. And further, to know the kinetics, like any electrochemical reaction, as it's going through 2 electron and 4 electron process, that oxygen in various intermediate. So to know the kinetics further, we have studied the TAFL plot. So from the TAFL slope, you can suggest that the platinum carbon is showing around 60 millivolt per decay, and cobalt oxide, that is our catalyst, showing the 74 millivolt per decay. So although there is still difference, but which is very much comparable to the platinum carbon, as in cobalt oxide is a non-noble metal and low cost system. So comparatively by performance as well as economically is very good catalyst for platinum carbon. Next. So here is the comparable data where any electrochemical reaction, onset and halfway potential is a good parameter to know their performance comparison. So in here you can see the platinum carbon showing onset potential around 1 volt with respect to reference hydrogen electrode RHE, and halfway potential is around 0.9 volt. So here last one, that our catalyst cobalt oxide supported nitrogen of entangled graphene, who is showing around onset potential 0.95, and halfway potential is around 0.84 volt. So which is almost comparable and the better value compared to without support system like cobalt oxide and nitrogen of entangled graphene. Next. So here, as the electrochemical oxygen reduction goes through various intermediate steps, so further there is a oxygen to water formation going through also H2O2 intermediate step. So what percentage are H2O2 forming? Because H2O2 is it can degrade the catalytic performance, and because H2O2 has a parasitic reaction, so which can react in the catalyst, and the whatever the separator or membrane are using in the any kinds of oxygen devices, oxygen electrochemistry devices, so which can deactivate that. So that's why here we check the RRD experiment. That first one shows the RD experiment. This one is the RRD, ring rotating disc electrode. So here we have calculated the percentage of H2O2 formation and the number of electron transfer. If any oxygen electrochemical reaction, as first I told, the 4 electron process, but some cases what happen, there can be reaction can goes through the 2 electron process. So when it is 2 electron process, percentage of H2O2 is high. So here we check the percentage of H2O2 formation in case of, also we have compared with the platinum carbon. So the blue one shows the percent. In case of platinum carbon, the percentage of H2O2 formation is very low, almost 0%. But in case of our catalyst, although formation of percentage of H2O2 is around 6%, but which is very low compared to the rest of the reported catalyst, whatever they are in literature. Also the number of electron transfer in case of the platinum carbon is around 4, and our catalyst is less than 4, but still as the percentage of H2O2 formation is low, so which could be a overall performance for percentage of H2O2 formation, number of electron transfer is comparable to the platinum carbon. So can you know next? So any catalyst, not only the activity, but initially it can show activity, but as we are doing in electrochemically, that Hertz condition at particular alkaline pH and applying the potential. So there are two main things, the potential and the alkaline condition. So how long it can be stable. So that is called durability of a catalyst. So here we have checked the durability by also we have done the cyclic voltammogram study for a 5,000 cycles in oxygen reduction potential window. So here after the 5,000 cycles, what we observed that here in platinum carbon, after 5,000 cycles, it's showing it's giving the 40 millivolt loss in the halfway potential. That means it affecting by the alkaline and potential condition. But in our catalyst like cobalt oxide supported nitrogen of entangled graphene, the shows the 12 millivolt only shift in the half potential. There are not that much change in the onset potential. So this lower degradation of our catalyst because of in platinum carbon there is only carbon, that is not graphitic carbon. So from this durability study, we got what is the importance of graphitic carbon, and our catalyst, the whatever we have prepared, the 3D carbon, there is a significant stability also there in our catalyst after the durability study. Can you go next? Finally, we have done the zinc air battery study. So this is our this is the first primary zinc air battery where only discharge things we have studied. So figure A is the demonstration of the zinc air battery where zinc using as a anode, and the catalyst whatever we have prepared, the cobalt oxide supported nitrogen to entangled graphene coated over the carbon and using as a cathode, and in between one separator or using as a using an aqueous solution of 6 molar K which are using for a electrolyte. Then we have checked the polarization plot. So in any kinds of devices, there are few things we are measuring that polarization plot of the specific capacity and how long it can perform. So first figure B here, you can see the polarization plot. So here our catalyst is showing around 210 milliwatt per centimeter square power density, which is high compared to the state of the art catalyst. So why this much high value is coming, although they are on half of potential, half RD level performance is low. So although there are no direct relation between the half cell and the full cell study, because we are comparing with respect to reference, and some cases we are using the aqueous media, but sometimes in device level solid as well as liquid media we are testing the performance. So here you can see that because of the 3D structure of the carbon, so in the when current density is around 250, here you can see the change is observed. Previously the OCP is coming very less compared to the platinum carbon, but there is a cross section between around 250 milliampere per centimeter square current. There is that is called ohmic region. So that portion's mass transfer is high because of the 3D nature. So overall performance is affecting their performance also. So further we check the how long it can give the performance. To know that, we have done the discharge rate with minus 10 milliampere per centimeter square. In figure C here you can see the 20% platinum carbon first discharge after 3.5 hours it started discharging, and almost 4 hours it completely discharged. And in our catalyst also, although there is discharge point is sudden discharge is there, but it is above 4 hours, like almost 4.5 hours it's giving the completely discharge performance. In figure D, you can see the specific capacity, how it's giving the performance. So here we have calculated the specific capacity in case of our catalyst, 20% with respect to 20% platinum carbon. So the specific capacity for our catalyst is giving around 475 milliampere per gram, which is higher compared to the state of the platinum carbon, which is giving almost 450 milliampere per gram. Further, we have demonstrated the device also in our real cell study. Although it's showing the LED light, it's lighting up almost 10 to 12 hours. It continuously giving the light after combining these two cells together. Next. So here is my conclusion that how we are getting the performance. One is the main important thing is the 3D carbon are using which giving the acting as a better support. And second one is the nano rod, whatever we are preparing the cobalt oxide, which is very good electronic transport property. And third one is that because of the spinel structure, the presence of the different metal oxidation state also, which are participating very good electron transport mechanism, as well as the cobalt oxide and nano rod. There are, as the nitrogen graphene is a 2D structure, so there is a good combination within the cobalt oxide, nano rod and 3D graphene, giving the higher loading and the comparable performance of the platinum carbon. So next. Okay, so yeah, thank you all for listening me. And this is our group. Where I'm doing the PhD. I am actually final year PhD student. So I'm from NCL Pune, India. Thank you.
Yes, thank you for your presentation. Thank you for your excellent presentation, Nargopal. Thank you so much.
Thank you.
Yes, yes.
Yeah. Nargopal, how did you manage with the nanorods, the structure? And what is the material that you have used for nanorods?
Actually, what we did, their ammonium hydroxide we are using as a nitrogen doped or as well as the reducing agent. So although we are controlling the pH through the ammonium hydroxide. So what we did, the ammonium hydroxide we are using with various pH range from using from 10, 11, 10.5 that way. So we got
No, I'm not asking that part.
Okay.
I just want to know, you have used the nanorods.
Yeah.
So how did you get that nanorods? What is the material that you have used for the nanorods?
Okay, materials I've used the cobalt acetate I'm using. Right?
For the preparation of the
Yeah,
nanorods?
Yeah, cobalt oxide I'm using.
Now, experimentally, that because first of all, nano itself is a so small scale. So, is it that what type in the market you will get that nanorods, this one, or how do you synthesize that one?
Yeah, there actually what finally what nanorod width and the length we are getting, which is around 12 nanometer in the width, and the length is around 120 nanometer. So that length and we are getting the nanometer.
You will prepare in the lab, or you will
Yeah,
get
I have prepared all the catalyst. Yeah.
Okay.
That.
Very great. Okay, nice presentation. Nice presentation.
Okay, thank you so much, Nalgopal. Thank you. Concludes the last talk of our conference, and I would like to thank all the speakers who have made this conference a success with their valuable presentations. And I request chairman of the conference, Dr. Per Lothman, to give his words about the conference.
Yeah, I will happily do that. I guess you can all hear me.
Yes.
I must say that it was a very, very impressive conference with a wide a spectrum of different topics and covering several different materials science and materials engineering related fields. So I think we can all be very happy that this conference was organized, as well as we can all look forward to the next conference coming up in, I think it is in November, right?
November 12 to 14.
Yeah, exactly. So I hope that all of you will join the conference again. And if I may add a couple of remarks, maybe, I think we have, we should look at the title of the conference, Material Science and Engineering, Progressing into the Future. We are most definitely progressing a big leap forward, a big step forward by this conference into the future. There's no doubt about that. And I hope and I believe that the next conference will take even a couple of more steps. If I may add a little short comment on the content, I think it would be a good idea also to, how should I say, well, one thing that I was stressing in the introductory speech, and that is the interdisciplinarity, as well as apparently sort of non-classical foreign topics such as biology and also medicine. We had some talks going in that direction on this conference, but I think we can even add more to it. And not only that, we have several topics that can be addressed in the future that are interesting for the material science community. I'm thinking about metamaterials and also smart materials, intelligence materials, even wise materials. We heard about shape memory materials in this conference, and that is actually a class of smart materials, one can say. And I believe that this conference was a very, very good start, and I'm looking forward to attending the future conferences from the Global Scientific Guild. I think and believe that we are progressing into the future. This conference was most definitely a success and a big leap forward by progressing into the future. Thank you very much. It was my pleasure to be the chairman of this conference, and I'm looking forward to see you all again in November. Thank you so much.
Thank you so much, Dr. Luthman, for your kind words.
Thank you.
Thank you so. Yes.
Yeah, am I with? Wait, just a second. Yeah.
Yes, actually, please.
Yeah. So, first of all, thank you so much to the Global Scientific Guild, to you, Mr. Nawaz, also, and to the chairman of our the conference, Dr. Paul Othman, for providing all the experienced scientists, experienced researchers who are having expertise in different fields, and for providing young engineers like me to express my research, to express my research in this very successful conference. I believe that the successful conference has been very successful. I also believe that I was able to present my work in a very good way. I also believe that everyone else here comprehended it in a very easy manner. And I also congratulate all others, experienced researchers, young engineers, PhD people, for showcasing their hard work in this successful conference. Thanks a lot.
Thank you so much, Akshat, for your kind words. Thank you.
Okay, I would like to thank once again the organizer of this wonderful event, and thank for invitation to take part in this forum, scientific forum. And it was my pleasure to take part, and it was a pleasure to hear and to see very interesting presentation and very different fields and very modern and actual subjects. So thank you very much once again for the organizer and the Global Scientific Guild, and to wish you much success in future, and see you in future again. Thank you.
Thank you so much. And thank you all these speakers and participants for making this conference a success. Our next conference will be in November from July 12 to 14. And I request all the participants to participate in our next conference also. And I wish all the best to all the participants. See you in November.